Depending upon your geographical location, good morning, good afternoon, and good evening to all the esteemed guests, senior and young participating scientists joining us virtually from different parts of the world. It is the matter of great privilege for us to extend you all a warm and cordial welcome to the third day of the 19th International Online Conference on Mathematical Sciences for Advancement of Science and Technology. In short, we call it MAST 2025, organized by the Institute for Mathematics, Bioinformatics, Information Technology, and Computer Science, having branches in Sweden and Japan. Today, we are now going to start the data science workshop, the third day of this data science workshop. And we are fortunate that amongst us, we have Vishwajit Pal. So before I start giving a brief introduction about Vishwajit, let me give you some of the references of this workshop. Like at this end of this workshop, that means after the talk of Vishwajit, there will be a short question answer type questions that would be shared through YouTube. The participants will have to appear for this exam, those who want the completion certificate. Those will obtain marks at least 50% of the score. They will get a completion certificate. Otherwise, there would be other links, only participation certificate. That means people may gather two certificates. One is participation certificate, those who have significantly participated in this workshop for the last 3 days, and also get the completion certificate if he or she can score at least 50% of the score. So that's all about this session. And now it's my great pleasure to welcome Vishwajit. And before that, I would like to give a brief introduction about Vishwajit. Vishwajit brings over more than 10 years of experience in delivering high impact data science and data engineering solutions, product development and consulting services, primarily in retail sector. Currently, he serves as the director of data science at Nuven, the customer health division of Johnson & Johnson, where he leads the development of AI, GenAI based applications and driving innovation at the GCC level. Vishwajit holds a master's degree in applied statistics and informatics from Indian Institute of Technology, Bombay, and bachelor's from mathematics from Presidency College, Kolkata. So currently I am from here. So it's my great pleasure to welcome Vishwajit, and without any further delay, may I request Vishwajit to take over the session. So Vishwajit, the session is yours.
Thank you, sir, for a great introduction. And yes, I belong to the same department of which Professor Valedictory is the HOD right now. So it's a great honor, sir, to speak in this eminent conference which you host. So let me just share my screen. Give me a second. Sir, is my screen visible?
Yeah, it's visible. Yeah.
Yeah. So again, good morning, good afternoon, good evening, depending on which part of the world you are joining this conference. So what I will do in next 1 to 1 hour 15 minutes is basically talk about how we implement an end-to-end machine learning projects or solutions or product, whatever you can call, in the industry. Now, if some of you are already followed the last two talks about agentic AI and optimization, which my colleagues have given in the last 2 days, so they talked about the specific algorithm parts, right? One around agentic AI, another around optimization. Now, what I'm going to do here is I'm going to bring everything together, and especially from a machine learning lenses, and will explain that how end-to-end we actually work. So let's start a little backwards. Now let's start from the point that why machine learning project fails. And there is a staggering stat around it, which McKinsey keep on publishing, and the numbers are actually very high. Means the latest number which I have seen I think last year, it says that around 18 to 20% of the AI ML projects shows the light of the day, which means that it goes into the production. So around 80% of the projects what we do typically ends at a proof of concept phase. Now the question is why, right? So, so what I've listed is basically the 6 main reasons why the ML project fails. Obviously, these are not the exhaustive list. There are some others as well, but these are the primary ones. Now, the first reason is that we typically, a lot of times when we start work, there are no clear business problem defined. Like, let me take an example. Now, a lot of time data scientists start working saying that, hey, I want to build a churn model. However, we are when the data scientist starts, many a times they doesn't know that, okay, I build a churn model. It actually tagged that, hey, these are the customers which have the highest probability of churning. But then what action need to be taken in order to retain those customers, that part is not clear, right? Because from a business standpoint, this may not be one of the top priority project or top priority problem area which they want to focus on. So what happens is that even if you build a great solution, the adaptability is very low. So essentially, if we don't have a clear business problem or the business alignment, typically that's where one of the reason where the ML project fails. The second aspect is about the data. Now, as we all know that data is the main fuel of anything you do in the AI ML space, right? Now, if you have a limited data or you don't have a great quality in terms of data, or if you don't have a much good understanding of the data, then eventually, anything you build on top of that will be very suboptimal. So there is a very known phase in the data science world is that a garbage in and a garbage out. So if your data is not great, then whatever you build on top of that will not throw the substantial result. It will throw garbage only, right? So having a good data quality is a major need or ask of any AI ML project. And the reality of the fact is not every time we get a great data. So that's the second reason. The third reason is a very interesting one. So as a data scientist, we have this tendency of straight away getting into more complex algorithms, right? Which are right now in trend. Like for example, neural network is a very interesting problem area or an interesting algorithm. However, not all problem needs a sophisticated algorithm like neural network, right? So what happens is that at a proof of concept or an experimentation stage, you might use neural network, but when you're actually scaling it or taking the solution to a deployment stage, then scaling a neural network may not be that easy. Means not only from an infra standpoint, but also in terms of cost, it might shoot up. However, a lot of time what we have seen is that a relatively simple model works almost equally like a neural network, right? And those needs lesser infra, those needs less cost, and you can do and the algorithm does similar, if not better, work than a neural network. So essentially, assessing the right algorithm is one of the key requirement. Now a lot of time it doesn't happen, and that is one of the reasons why the ML project fails. The fourth is around choosing the right evaluation metrics, and I'll give you a simple example. Now, say if you are building a classification model, it's a 1 and 0, you need to classify them correctly. And say you have 100 data points, right? And in that 100 data points, you have 5 ones and 95 zeros, basically. So 5% are your occurrence and 95% are not. Now, you build a great model, it gives you an accuracy of 94%. You will say, wow, you did a great job, right? But just if you think from a common sense standpoint, if you just put 0 in all the cases, you don't have to do anything, you just put 0. Because you have a 95% zeros, you will get a 95% accuracy, right? So your commonsensical or just putting 0, you're getting a 95% accuracy vis-a-vis when you're building a model, you're getting a 94% accuracy, right? So it's very flabbergasting, right? But the what exactly happening is that in cases where you have an imbalance problem, where you have a lesser one, accuracy is not the right measure, right? So what essentially has happened here, that we have actually chosen a wrong evaluation metrics. So this kind of a this is also ties back to one of the reason why the ML project fails. The fifth one, which is, I think it's related to somewhere with no clear business problem as well, that there is the deployment and adoption plan are not properly defined. That means we build a great solution, but how these solutions will be used, that part is not very clear, right? And the example I've already given from a churn model standpoint. And the last one is, you build a great model, you have a proper business problem, you have adoption as well, you put the model into the production, but you don't have a proper feedback mechanism in place or a monitoring mechanism in place. Now what it happens is that with time the performance of the model typically goes down, and there can be multiple reasons. One of the reason is typically what we have seen is data drift, that the entire data has changed a bit, and that has impacted the performance of the model. Now if you don't have a proper monitoring mechanism in place, what will happen is that we will not be able to track the performance of the model over time, so we will not be able to intervene at the right time when the model is going down, right? So having a proper monitoring loop, and obviously vis-a-vis that, once you are falling down, if we don't have a proper feedback loop in place, then we will not be able to capture the downside of the models and try to like improve the model in an iterative manner. So that particular mechanism, as it is not there, will impact the results. So essentially what it ties back to, so the AI ML project success, 20% depends on the modeling, but the 80% depends on how you are framing the problem, what is the data, what kind of a deployment adoption plan you have, right? So this is the reality. So only focusing on algorithms might not solve this particular problem. So now the question is, what is the solution to it, right? Now that is where we'll get into a framework. This framework is called CRISP-DM. It's called Cross Industry Standard Process for Data Mining. Now, this particular framework is not a new framework. It has been, I think it came into existence around 1996. So it's quite old. But the interesting thing is that it's still one of the mostly wide framework what we typically use. And this takes care to a certain extent the 6 pitfalls which I talked about. CRISP-DM has 6 key phases. Number 1 is business understanding. So it's about defining the right problem. Now, if you recollect, right, the first problem was that there is the business problem is not properly defined, right? So that's what the first phase of the CRISP-DM do, that you need to define the business problem in a correct manner. Second is about data understanding, that so it's basically start off with the data discovery, that what kind of data we have, are these good enough to solve this particular problem, what about the quality of the data, all those things are assessed in this particular phase. So if you can recollect the second pitfall, which is about poor data quality and understanding, this is where this particular phase, which is about data understanding, comes into the picture. Then once you have the good understanding of the data, so the third step about you have to clean the data, you have to create a lot of features, and eventually get it ready for building the models, which is basically either statistical model, it can be machine learning, it can be deep learning, even it can be a generative AI as well. The fourth phase is about modeling. Obviously, this is the phase where we build and train our models. Now, this is again where we talked about The algorithmic part over focus on the algorithm. So this is the place where we actually need to evaluate a lot of questions. That means, what is the right model to be used in this kind of a problem? Do we really need a complex model, or this can be solved with less complex problems, sorry, less complex algorithms? So all these questions gets answered in this particular phase, and finally you will build the models. The fifth one is about evaluation. Now, evaluation happens at two levels. One, at a model level, that means we have different goodness of fit at a statistic for the statistical model or ML models. And we also assess or evaluate our output at a business level as well. That, hey, you know what? Maybe this particular model is satisfying the ML goodness of fit. It's actually doing great. However, the output doesn't tie up with the overall business KPIs. So that may not be a great solution, right? Obviously, the perfect solution what we look for is the solution which align both with the modeling KPIs as well as the business KPIs. So that's the stage where we focus on, and we take care about the wrong evaluation matrix problem what we have seen earlier. Last but not the least is where we put the model into the real use, or we scale the model for a bigger use case, or essentially we deploy, right? So that is the last phase. Now, if you see the diagram on the right hand side, the steps doesn't work sequentially. So there are like different arrows here. So what happens is that we start up with the business understanding. So once we understand the business problem, we go and do the data discovery or data understanding. Now, a lot of time what happens is that the data which are available or usable may satisfy or may answer a part of the business problem, may not be good enough to solve the entire business problem. So what we do is that we go back and then we change our scope. That, we started off with problem A, and based on the data availability and the data quality, we feel that maybe A is not what we can do. We can do a partial of A, maybe A1, right? And that's become the newer scope of in terms of solving the problem. So once we actually complete this first and second steps, then obviously we go into the data preparation, and it's a unidirectional. That is, like it's a straightforward data cleaning. You create different engineering features and etc. etc. Now, once we create this particular, or once we are done with this particular step, then we start building our models. Now, again, there is a to and fro, because what happens is that you create the features in a certain way, you build the model, and then you find that, hey, maybe we need to build some additional features. The features and the current features are not adequate enough to come up with a certain accuracy level. I'll give you a small example. Like a lot of ML model, we use a variable called discount percentage. Now, if you see discount percentage is like sometimes you give 10% discount, sometimes 20%, sometimes 25%. So it's more of a continuous variable. But a lot of time what we have seen is that if we use the variable as a continuous variable, then it doesn't yield it doesn't give a great accuracy. But if you break it into bins, say for example 0 to 10% one bin, 10 to 20% another, 20 to 30%, like that way, the fit is better. So essentially what my point is that the data preparation, or especially the feature creation and the modeling, is again goes hand by hand, and that is why you will see a to and fro direction. Now, once we build the model, then we go into the evaluation. Now, for the evaluation, we also need the business KPIs, right? As I mentioned. So it also ties back to the business understanding part as well. And finally, when we hit the right KPIs, both from business as well as the model standpoint, then we finally go and deploy. And this particular process overall is also very cyclic, because once you deploy, you monitor. Maybe after 2-3 months, you have to do a fine tuning, and then based on the accuracy, you again do this particular process once again. So it's a more cyclic in nature. So what makes ChrisDM very suitable for a ML kind of a AI ML kind of a scenario is, first of all, this is not a model first framework, it's a business first framework, right? Because eventually what we solve is a business problem, right? So we need a framework which ties back to the business. Second is it is very iterative and feedback driven. And that is a major differentiation from any of the software industry frameworks. Because ML by nature is very iterative and we need a feedback loop, right? So we need a framework which will actually cater to these two needs, and ChrisDM fits the bill perfectly. So that's why the ChrisDM is a very apt and most widely used framework in terms of solving data science problems. Just a recap, because I've talked a lot, so let's quickly recap. So ChrisDM, there are 6 major phases. Number 1 is business understanding, where you define the right problem. Then comes the data understanding, where we do the data discovery, we explore, we validate. Then we come to the data preparation, where we clean the data, we create different features. Then comes the modeling, where we actually build and train our models. The 5th stage is about evaluation, where we validate the outcome, both from a ML or statistical goodness of fit standpoint, as well as from the business KPI standpoint. And then finally, we get into the deployment phase. There are 2 interesting characteristics of ChrisDM. Number 1, it's a business first framework, not the model first. And second is it is iterative and there is a feedback loop here. Okay. Now what we will do is basically we will go deeper in each of these phases. One lenses is from an understanding standpoint that what each phases do, and second is about how mathematical concepts comes into each of these phases. Okay, so let's go to the next one. Now what we will do is that we will go through all these phases with keeping in mind one example. One example what I have taken is basically a customer churn prediction use case for a telecom company. Again, customer churn prediction is a very widely used use case in the AI ML space. And the goal here is to predict that whether a customer will leave the company in the next 30 days. So that is what we need to predict. Okay. Now, let's go to the phase 1 or the step 1, which is about business understanding. So the theme of this particular phase, as I mentioned before, that we need to understand what the problem business is facing and how ML can help to solve that particular problem. So that is the key theme of this particular phase. So what are the key questions what we need to get the answers? Number 1 is what is the business objective? Number 2 is what decision will be taken if we actually build a good model? Right? So based on model's outcome, what kind of decisions are we talking about or will be taken by the business? And third is basically how the success will be measured, right? So now let's map this to our use case of churn prediction in the telecom industry. So our business problem is that the customers are leaving, which eventually will tie back to the revenue, loss of revenue. So can we actually identify the customers who are likely to churn in the next 30 days, right? So that is what the business problem ties back. Same goes with ML objective that, hey, can we predict customers who are likely to churn? And once we predict them, then what we will do is that we will try to offer discount. We will try to retain them, right? And retaining them can be discounts. We might call them individually and try to understand what kind of problems they're facing and try to rectify. So more personalized service we can provide it to them, right? So so basically our key question map back to our use case. What is the output of this particular step? Number 1 is a clear problem statement. And second is basically to determine what are the business and ML success metric we are talking about. Now, just to focus on this, how will success be measured, right? Now, just imagine we build a model and it actually it got deployed and said that it identified 100 customers who are going to churn in next 30 days. We actually talked to those customers. We offered discount. We called all the possible thing that we did, and we find out that out of those 100, maybe 90 has already churned, and 10 we could retain. Right? So is 10% retention a good success criteria? May or may not, right? So what is that percentage what business is looking? Say maybe if business is looking, hey, I want a solution which leads to a 40% retention, and I gave you a solution which led to a 20% retention, right? So maybe in terms of solutioning, it is good model, but overall it doesn't meet the business need, right? And that's why the success criteria or the business success metrics is a very critical one. This particular phase I really liked. It says that if you cannot explain the problem in simple words, don't start coding. And the analogy to it is when you actually solve a problem, you're solving a problem, right? In mathematics or statistics or econometrics, whatever, wherever you are or whatever you are studying. If you don't understand the question, so there are typically two outcomes what I've seen. Number one, you did it without your understanding is vague. You went ahead with the solution. You most likely ended up with a wrong answer. Second possibility what I have seen is basically you started doing it, you got stuck in the middle, you went back, you see the problem, and you say, hey, you know what, this was not my understanding was not sufficient. So whatever I did for say 10 to 15 minutes is actually what I'm not supposed to do. So already the time has lost, right? So we have already spent 10 to 15 minutes. So eventually, there are two outcomes. One is either their answer will be wrong or you will be losing time. Hence, just like in the exam, your understanding of the question is very important to get the right answer. Similarly, in when you're solving a business problem in the DS or ML space, until unless you have a very clear understanding of the business problem, if you start coding, same thing will happen that you will stuck in the midway, and in the middle you will realize that whatever you are solving is not what maybe partially you have been asked for. So a majority of the work what you have done so far has gone for a toss, right? So it's a loss of time, and sometimes if you continue doing it, you ended up coming up with an outcome which maybe the business is not looking for. So there is a mismatch of the business expectation and what we have generated, right? So that's the reason it's a very powerful phrase that if you cannot explain the problem in simple words, please don't start coding. Now let's get to the mathematical part. So if I map back to from a the business understanding to from a mathematical or statistical lenses, what exactly what we are supposed to do here, right? So essentially the key question turns out to be, okay, what is the output variable we are looking for? So in this case, the output variable what we are looking for is that, okay, y is equal to 1 for the customer who have already churned, and y equal to 0 where the customer will not churn, right? So that's the mathematical conversion of the business problem. Second is that what are we looking for here, right? So we want to identify customers who are likely to churn. That means what we are trying to do here, we want to calculate the probability of churn for each customer. And then out of that, identify the customers who have the highest probability, right? So that's the mathematical conversation, right? And finally, what the success means, right? And here the success means is that we need to minimize the false negative. And I'll come to the false negative and recall in the subsequent slide when I'll be explaining the evaluation criteria. But for the time being, so this is the mathematical part that, hey, we need to minimize the false negative. So that's what the success looks like. So this step, if some of you have done optimization, you can easily tie back with defining the objective function. In the optimization, right, we define an objective function and then we actually have some constraint. This step is almost similar to that we define an objective function, where in this case is basically estimating the probability of the customers of churning, and then we have a certain constraint which definitely are the certain features here. So this is the way we tie back. So this is basically a connotation between the business understanding and then what kind of mathematical concepts are getting used here. Now let's move to the next step. So once we establish the business understanding, let's get into the data understanding, right? So in this case, what the outcome? Simple outcome is basically we want to explore and understand the data. That's a simple outcome. The output are data description and some insights about the data, right? What are the activities what we typically do? We collect the data from different sources. We try to understand what are the different data types. We identify the missing values and if there are any imbalance in place, and then we perform some basic exploratory data analysis just to understand how the data are. In our case, like typically it's just a very small snapshot of the data what we use while predicting the churn. Customer age and gender, monthly bill amount, because it's for telecom industry. What are the users data? What are the contract type? Whether it's a prepaid or a postpaid, and then whether obviously the churn is yes or no, especially for the train data set. So this is the straightforward, the steps what we do typically in terms of the data understanding. But it's a very important step because we should never trust the data blindly. We always need to explore it, because until unless we have the understanding of the data, proceeding without having that is a sort of a suicidal mission. Means it more in 99% it will lead to a big failure, right? And that's the reason why the data exploration or data understanding is a very important step. Now let's see what if we can convert this into a mathematical concept, right? How exactly it looks like. So the data, and especially in the structured data area, we can easily write it in a metric form. So x is the set of features. So x1, x2, xn, these are all features. So x1, you can call it a monthly bill amount. X2 can be tenure. X3 can be number of complaints. And this xi is basically one row of data. So x1i, x2i, and xni are basically the value of those features for the ith row, right? So if you can just easily visualize, if there are say m customer and n features, essentially your data is nothing but a m cross n matrix. That's it, basically. So you can easily visualize the data in terms of metrics. Now, it also ties back to a lot of statistical question. The first question is, what are the distribution of each of these xi's? Means each of these feature, what are the distributions, right? So for example, the monthly bill is definitely a continuous variable. So we'll so we can easily get the distribution of the this particular feature by understanding their mean, variance, skewness, and other central tendency measures. X2, which is a tenure, will be a more discrete variable. Number of complaints against a discrete variable, so you can always get some distribution of these variables, right? The second most important concept in this case is, what is the correlation between xi's, what is the features, with the target variable? Because with that, you will be able to understand that what kind of relationship does your target variable y holds with each of these x's. Again, y, if you remember, you have already defined y is equal to 1 when customer will churn, 0 when customer will not churn, right? So here, there is a correlation study. And in our example, and then we also have we can easily get the balance imbalance, and I have a small demo where I'll show it how exactly all these things, how you can do it in Python. So in the example which I'll show it, the churn rate is around 27%. So it's like a 27 and 73%. So essentially there's a bit of imbalances there. There are certain features which have a missing values, and then some of the distributions are also skewed. So we can see some of these in our data. Now, this is a step where we get some descriptive statistics and do some exploratory data analysis, right, from a mathematical or statistical concept standpoint, right? Now let's move to the third, which is about data preparation. So the second step is about data exploration, that we explore the data sources, we do the basic checks and balances in place, we integrate the data, do a basic EDA, and then obviously then we get into the data preparation. The missing value treatment can be done either ways, basically. You can do it in the previous step as well. Sometimes we do it in data preparation as well. Same goes with outlier, because what happens is that these are all comes under the data cleaning step, right? You are cleaning the data. Sometimes you have a high outlier, so either you cap it or you drop it depending on the situation. Then what we do, a very common practice is about we encode the categorical variables. We convert one of the most widely used encoding is a one-hot encoding. We convert the categorical variables into one and zeros, and there are other ways as well. Then we create a lot of new features. Like for example, as I was mentioning before, like discount percentage, right? If you remember the example which I cited in the slide one, that either we can use as a 10, 20%, 25%, or else we can also convert that into bins. So that is basically you are creating a new feature, right? You are creating a new bin variable. The other things are also we do a lot of variable transformation. Like for example, log transformation is a very widely used. There are methods like box-cox transformation, what we typically use to transform the data. So, and then lastly, what we do is we split the data into train and test, because train data is where we train our model, and then we test our model into the test data. So these are the typical activities what we do. I think in our case, the example which I'll show that hey, there are some missing value, and we actually did a quite quickly a missing value treatment. We encode some of the categorical variable, as I was mentioning, the one-hot encoding, converting into one and zeros. We will be creating as new features as I talked about, and then finally we split the data into 80% train and 20% test. Right? Typically, that's the industry standard. Sometimes even 70-30 also gets used. So the net output of this particular step is we get a clean training and test data set, because these training data and test data will be used for our modeling, right? Now, the most interesting thing in this particular phase is this is the step which takes the most amount of time in an ML project life cycle, because this is the gateway. And you recollect that phase of garbage in, garbage out. If we don't fix this, or if you don't do this particular step nicely, or a very in a detailed manner, taking care of a lot of things, then we might not get the outcome which we are looking for. That's the reason why we spend, as a data scientist, we spend a lot of time in this particular phase. Now this is again a very heavy mathematical step. Now I'm just mentioning few of them, but the key operation, as I mentioned before, that one is a missing value imputation. There are different methods of missing value imputation. These are very statistical / mathematical methods. Outlier detection, again a very core concept of statistics. Variable transformation, as I mentioned, we use a lot of polynomial transformation, we use a log transformation, we use different box cost transformation, and so many. Again, it's a very heavy mathematical and statistical phase. And then definitely the feature construction. Like as an example, if you see, I was talking about, so there is a tenure variable in our data. So what we do here is that we created a simple bucket that if the tenure is less than 6 months, then you add 0 and 1 otherwise. Simple mathematical operation, but it sometimes it works wonders. Then in a lot of ML model, we need to normalize the features. What the normalization means is and again there are various methods of normalization, but this is a most widely used normalization method, where we subtract our actual value with the average value, and then we divide it by the variance or the standard deviation. Train and test, what I mentioned before. So essentially my train and test data should be mutually exclusive, right? So obviously the train and test data union is the total data set, and the intersection of the train and test should be a null set, right? Because that's the fundamental. So this, out of the 3 phases what I talked about, this phase is a more heavy in mathematics in terms of the concepts. And it's as I mentioned before, it's a very, very critical phase. Now let's quickly move to the next phase, which is about the modeling, which is our core, right? As a data scientist, this is our core. Now this is basically all about statistics, mathematics, ML, everything. So this is what typically econometrics, mathematics, especially econometrics and statistics students study. Mathematics also, we have papers around that, right? So obviously I'll not be going deeper, but this is where we are building our machine learning model on the trained data, and then we do the testing on the test data, right? Typical activities, we start up with a simple model, we compare multiple algorithms, we tune a lot of hyperparameters. In this particular case, because it's a classification problem, we can use logistic regression, decision tree, random forest, XGBoost. And the final output of this step is a trained ML model. Again, this is almost a 60-70% of the syllabus of anything what you guys are studying as a statistics or economics students, right? So this is the core. You can convert anything and everything here into mathematical. I'm just giving this as an example. So if you see the logistic regression is nothing but it's a conditional probability that you need to measure or estimate the probability of y equals to 1, which is our event, in the presence of all the features, right? And the typical equation of a logistic regression is this. So 1 over 1 plus e to the power minus beta 0 plus beta transpose x. Now, beta 0 is basically, all the betas are the parameters. Beta 0 is the intercept. And beta 1, beta 2 are the parameters for each of these features. How to estimate the features? Now, there are a lot of techniques. You have gradient descent. You can actually use the maximum likelihood in order to minimize the loss function to get the betas. The advantage of logistic regression is that all the betas are interpretable. So you will be able to understand and explain each of the betas what's happening. It's a convex optimization problem. So your local minima is a global minima, and hence things becomes very simple. Means in terms of convergence. And it's a very strong model. It's a very well-known model. It's there for since ages. And a lot of times logistic regression do wonders. So it's a very strong baseline model. So especially in the classification problems, again, logistic regression is used in classification. Typically, we start off with the logistic regression and the results act as a baseline. So anything we build on top of that, or any other model what we build, sort of that needs to beat logistic regression. And a lot of time, believe me, it's not that easy. So this is a very, very heavy mathematical step what we do in the modeling, because that's the core. Now let's go to the next phase, which is the fifth phase. This is about evaluation. Now, as I mentioned, the evaluation happens at two levels. One at a ML level, which is machine learning level, and also at a business level. Now, because we are talking about the classification problem here, the common evaluation metrics are the confusion matrix, precision recall, and ROC curve, and I'll go in detail in the subsequent slides, in the next two slides actually. And I will also explain why some of the measures are important. You remember one of the major problem was identifying the right evaluation matrix, and that is what I'll show how. Output of this step, obviously this is a step where we finalize our model based on the accuracy. And we also have generate a detailed evaluation report, because this is the where we showed it to the business that how the results looks like, whether it is aligning with your numbers, your goals, or your expectation. A very, very important call out. You should choose metrics based on business impact and not just accuracy. And if you recollect again, I talked about that example where you got a 94% accuracy, but that's not a good enough, right? Means it's basically, even with a normal commonsensical approach, you would have got a 95%. And I also talked about the 10% or 20%, right, about the churn, and it may not always work well for the business, right, because they might be looking for 40 and 50%. So I think this is a very important call out, that you should choose the metrics based on business impact and not only on accuracy. Now let's go a little deeper into each of these two metrics. One is a confusion metric. Now what it does, it's a simple metric. If you see, you have, because it's a classification, so you have a 0 and 1, and these are all actual 0 and 1. You ran a model, say in this case logistic regression, and you have predicted, so you got a predicted 0 and 1, right? Now obviously the diagonals, which is the true negative, where you have an actual and you predicted 0, perfect, that is what we expect. You again 1 1, again it's a true positive, because obviously you predicted the positives correctly. Now the interesting is the other two, right? So what does false positive do? What does it mean? it means that actually this customer didn't churn, but the model says that, hey, they have churned, correct? And the false negative is basically what it says, that actually the customers have churned and the model says it has not churned. Now, what the important thing what you need to do is basically you need to understand from the business context or from the problem context, out of these two, which is a more important problem to the business, right? Now, if you see the false negative, what false negative suggests is that, like they have so essentially what model is doing here, that they are not able to identify the actual people who might churn, right? So what is happening, that if I use this particular model and if my fn false negatives are on the higher side, that means we will actually ignore some of the customers who have a good possibility of churning, and that is a very costly mistake in for this particular problem, right? Vis-a-vis what false positive is saying, that there are certain customers who are actually not churn, and we are actually there is a, we are identifying them as a churn customer. Now what maximum will happen, that we might extend some discount percentage to them, right? Because as per the model, they are about to churn. You might have a customized call with them. Now the cost of false positive in this particular case is not that much, right? So that means your cost of false negative is more than cost of false positive, and hence this triggered that what accuracy measure become important. Now these are, now precision and recall are the two, the parameters which comes out from the confusion metric. Now, if you see the precision definition, or let's start with the recall definition. What recall says is true positive divided by true positive plus false negative. That means your denominator is all the population who are actually been churned, and out of them, how many our model is able to correctly classify, correct? Precision is here true positive plus false positive. That means this is the denominator being that this is a segment which model is able to predict correctly as a churn, or not correctly as a churn customer, and how many of them have truly churned, correct? Now here, given the fact that the false negative is an important parameter over false positive, and hence the recall becomes the most important measure out of all this. So in this kind of a problem, and if you remember that 5% and 95% we talked about, right? Now in this kind of a problem, the recall becomes it's not the accuracy what matters. What it matters is basically your recall. So what this ties back, right, is ties back to these two concepts of that you need to obviously have a good criteria, or the good validation criteria in terms of precision, recall, and F1 score, which is a combination of the two. But out of all the three, or maybe accuracy is one more measure, out of these four, if you have to rank in terms of the business wise, then you have to pick up the model which is doing great in recall, right? So maybe you get a model which has a higher accuracy and recall is somewhere around second and third, and you got a model which has a number one in recall and number second or third in accuracy. Given this is the use case where recall needs to be important, then the second models precedes over the first model. And that is how you tie back the business metrics with the statistical or ML metric. Okay. Now, let's go to the second important evaluation criteria or metric, which is the ROC. Now, what ROC says, it's again ties back to your confusion metric. So now, let's go back to confusion metric once again. So typically, as an outcome of any classification algorithm, we get the probability, right? So you remember we defined the probability here, this one. So, we want to understand what is the probability of every customer to churn. So now, if we use a threshold of 0.5, right? So if more than 0.5, you are actually you are being classified as one. That means there is a good chance of churn. less than 0.5 is 0, right? So you will have a one set of confusion metric. Now, if I change my threshold to 0.7, then will the confusion matrix will remain the same or it will change? Obviously will change, right? Because your threshold have changed. So your entire precision, recall, every numbers is going to change. So the way the ROC curve gets created is you calculate the true positive rate, right, which is called sensitivity as an x-axis, and then the false positive rate, which is a 1 minus specificity as the y-axis. And every your thresholds are basically, as I mentioned, 0.1, 0.2, 0.3, 0.4. So every threshold will have a different confusion matrix, and you'll have a different true positive rate and a false positive rate, right? So that's the way you create you generate this particular curve. Now, this diagonal is basically the random guess. So if you don't do anything, you just like a flipping of coin, right? So you just guess it. This is what your diagonal will be. So whatever model we are building, ideally the objective is basically that it should be on top of this particular diagonal. Ideally, my true positive rate should be 1 and my false positive rate should be 0, right? So it should be on the top left corner. But this is what is expected out of it, this particular area. Anything below the diagonal is not what is expected. Obviously, that's a poor model. So that's why what we do is, that is where the area under the curves become important. So essentially we plot the curve, as I mentioned it to you, by changing the threshold. And then this entire green area is basically area under the curve. So area under the curve, 1 is like a perfect model. So you got 1 here. So entire area is like basically it's just a 1, your perfect model. 0.5 is essentially the discrimination, right? So anything more than 0.5 is a decent model. Obviously, as the AUC number goes closer to 1, that is what is expected, right? So a 0.9 greater than 0.9 is an excellent model. 0.8 to 0.9 is a good. 0.7 to 0.8 is a fair, and like anything lesser than that, we typically say that hey, it needs improvement. So these are essentially the two important measure which we typically use for classification problems. Similarly, every type of problems have different this kind of a measure. But what it entails to is just see how it's a totally a mathematical concept, right? You generate the curve, you calculate. It's a pure play mathematics what we actually do, right? So essentially that's the fifth phase, what we call as an evaluation step. Then the last one is about deployment. Now, as I mentioned, the deployment is about once we finalize the model, then we are putting the model into the production, right? We are scaling it, we are putting into the production. This is a heavy, it requires a lot of coding, a very advanced level of coding, because you are scaling, and I'll show an architecture diagram at the end, and then you will realize that how exactly, how much coding you need to know in order to build this kind of a scalable system. But the main thing what happened is that basically that, okay, you start deploying it, so you have to run. Now the objective of our case is so the probability of churn. Now this exercise typically happens almost once in a week. So you have to run this particular model once in a week. And then you have to publish this particular results in a certain consolidated form, in the form of a report or a dashboard, right? So these are the typically methods. And as I mentioned before, if you remember, one of the problem is, okay, you deployed, but there is no monitoring happening. So essentially, how the model is exactly performing in the deployment stage. Maybe in the development stage, you have hit a ROC of 0.8. That's a great model. But say after 1 month of run or a 2 month of run, are you getting the same ROC or same AUC number? Are you getting the same recall number? So until unless we have a proper monitoring method, if you recollect the last point, what I mentioned about monitoring and feedback, that is where a lot of model after putting into the production also fails, because the performance degrades. So we need to have a proper monitoring plan in place, right, in this particular as a step up, as a part of this particular stage. Again, a very important call out, one of my personal favorite, a model that is not used has zero value. So you did a great job in terms of the first 5 phases, but if you didn't put into the deployment, then it's basically of no use, right? Because your model is not getting used. So essentially, that's not what we are looking for, right? That is not what we work for. So that's why the deployment phase is a very, very critical phase. Some basics, again, some basic mathematical interpretation. It's not a very heavy mathematical phase, but like for example, if you flag customers, probability of y greater than 1 equal to 0.7, which we already do. And I was also talking about the monitoring, right? That okay, what is the probability of your new features or your new data, and compare it with the train data and the test data what we have done earlier, right? And one of the major aspect why it may not be equal or it has changed is because your data might have changed over the time. You can call this as deployment is more of an out of sample kind of a generalization what we do in this particular phase. So now if I bring everything together, right, and we map the CRISP-DM steps with the typical mathematical topic, business understanding is equivalent to a problem formulation where you actually form the problem. The data understanding is where you get into the probability and the statistics because you want to understand the distribution of the data, you want to understand the few basic stats of the data. Data preparation where you do a lot of linear and non-linear transformations, right? So that is where you use a lot of mathematical transformation operation here. Modeling, very heavy. That is what the core of statistics, regression, decision tree, time series, neural net, so on and so forth. So many different things are there. Evaluation, again, heavy mathematical process. As I explained about the confusion matrix, purely mathematical. ROC curve, purely mathematical, and there are so many other measures which are very, very mathematical in nature. And finally, the deployment, which is a very generalization theory of it. Now, let me quickly walk you through a simple demo. I have a simple demo prepared just to showcase if we convert this into a Python notebook, right? How exactly you do the step-by-step process, right? It is about problem solving. Sir, is my screen visible?
Yes, visible.
Yes.
Yeah, it's visible.
Yes.
Perfect. So again, let me just recap the 6 steps or 6 phases of CRISP-DM. Number 1 is business understanding. Number 2 is data understanding. Number 3 is data preparation. Number 4 is modeling. Number 5 is evaluation. And number 6 is deployment, right? So I will show, it's a very simple example, obviously, but I'll show how exactly we proceed with each step. Now, if you see the business understanding, right? So our business question is which customers are likely to churn in the next 30 days so that, obviously the retention actions can be taken. Our target variable is a churn variable, which is yes or no. It's a binary classification problem. And what is the business risk that if we miss a churner, then obviously it is a loss in revenue, right? And typically retention, getting the new customer is a much more expensive affair compared to if you're able to retain the customer. So essentially, retention is a very important phenomena in a retail, CPG, any world. A key metric, as I mentioned, recall so that we should not miss the churners. And again, I'll share this particular Python notebook. So I've taken it, the data I've taken it from the Kaggle, and this is the link of the data. So this is where we are defining the business understanding, right? So we define the business objective, we convert it into an ML, we define what are the key metric, right? What we are targeting here, and what is the data source. Now let's go to the next step, which is about data understanding. Now this is simple. I'm just importing some important library in Python. It's again across, not specific to this particular step. Then what I did is I read the data set. So this is basically the data set. If you see, it has some 21 columns. Columns like customer ID, it has gender, whether he's a senior citizen or not, some partner, whether he has a partner or a single. There are dependents and so on and so forth. There are a lot of different variables there. And then if you go and try to get the more information about the data set, you just need to use this syntax df info and df describe. So what info does is basically if it gives you, hey, you know what, there are 7,043 rows in this. And earlier also we got to know it's a 21 columns, right? So now if you convert this into a metric, what I talked about in the data preparation, it will be a 7043 cross 21 metric, right? That's the whole metric. If you go to the data variables, you will see that, hey, which are basically my type of variables, right? Integer is definitely numeric, some are text variables, so how the variables looks like. And then we also get some basic statistics of my numerical variables. So you say that there's a senior citizen, so there are obviously the count is 7043. What is the mean? What are the standard deviation? What is the minimum number, maximum numbers, and all. Now, one interesting thing here to note is if you see the data, we have the monthly charges and we have the total charges as well, right? There are two. However, the monthly charges is numeric. That's why obviously the statistics came. But the total charges are basically an object, right? So that means there is a issue in terms of data, right? That, hey, this is not correct. We need to change it. And that is exactly one of the major step of a data understanding, that we need to understand the data, right? Now, if you ignore this, so that means you will ignore this particular factors totally. You're not going to use it because it's object. So obviously model will not be able to take this as an object, right? So then we also, so that's the one observation, okay? Then the second is that because churn is our y variable, target variable, we just wanted to see that what is the proportion, right, in the data. And we see that there are 27% of yes and 73% of the no. Though I will not call it as a very highly imbalanced data, but partially it's like 1/3 and 1/4 and 3/4 kind of a distribution. So it's a little imbalanced data, right? So that is another insight what we got. Now, what I did, you remember I mentioned about the type of total charges. So here I actually change it to numeric. And then once you change it to, then now if you see the total charges has come, now it has a numeric now and it making senses. And again, this is one of them. There are a lot of other problems in the data which we should do. It's just for the demo purpose, I'm just showing it for one factor. So and the second, then the another concept I mentioned about missing values, right? So we need to see that, hey, we got the data, but whether it is usable or not, right, to us. So here we checked that whether there is any missing value or not for each of these variables. And what we see that there are some 11 missing values in the total charges, correct? So essentially these are the key observation what we got. Number one is the data is imbalanced because it's a 26% churn. Some columns are categorical and the total charges has a missing values, right? So these are the major observation what we need to now some we need to rectify or change. Some is mostly from okay, we just have to keep in mind so that accordingly we make the changes. Now moment you go into the now, so my data understanding is done, right? So then we are getting into the data preparation step. So data preparation step, the first step is definitely the straightforward one because there are missing values. So let's change the missing value. What I did, again, there are a lot of different ways you can actually impute. I just used a median value to impute those missing values, right? So once I imputed the median value, if you see there is no more a missing value in the total charges. So it has been taken care of. Then if you remember, we talked about encoding, right? Now encoding is like, for example, if you have seen the data, the churn variable is a yes or no variable. So encoding is one of the ways basically, okay, now we have to convert this into a numeric 1 and 0 because it's our target variable, right? Obviously yes and no can be a little tricky. So we just change it to 1 and 0. Just map it, yes is 1, no is 0. So now if you see, the churn variable has now become 0 and 1. So that's the impute what I'm talking about. Then what we did, a simple cleaning or data preparation is that, hey, I don't need the customer ID. So I drop this particular variable from the data set, simple drop this column totally. So now we don't have the customer ID. And then we talked about the categorical features and then encoding it, right? That one-hot encoding is one of them. So we converted the categorical features into dummies. So again, essentially what has happened, if you remember, if you recollect, right, there are 21 columns in the main data. We dropped one column, so it should be 20. Now we have created some additional features using the one-hot encoding essentially. So it's basically, again, it's what we are doing is converting some of the, so having those additional features, right? That is exactly what we are doing. And then finally, if you remember, the final step of the data preparation is splitting the data into train and train and test samples, right? And here, if you see, this is what exactly we have done. Test size is 0.2, means 20% is basically test, and remaining will be put in the train. So exactly what we discussed or what we actually went through in the PPT, this is what the steps were in terms of theory. Then these are the mathematical concept, and now we are converting this into a Python code. That's the way you execute. Now, once we done that, so we are done with the data preparation step. Now we are getting into the modeling step, right? And again, there can be a lot of modeling can be built. I have just used the logistic regression. So first step is about, we did the standardization. Again, if you recollect, we talked about the standardization, right? Standardization is basically you take out the mean and then you divide it by the standard deviation. So this is the same thing what is happening in the Python. This is just functions to do it. Once you have the standardized features, then what we did, we actually fitted the model, logistic regression. If you see, we have called the logistic regression model. Now, if I go back, we talked about the imbalance, right? One of the observation from the data preparation, or not data preparation, the data understanding step was that, hey, you know what, it was imbalanced data, correct? Now, this is where we are using a tag called balanced, that you know what, now because it's an imbalanced data, so we have to use a mechanism called balance. So it basically handles the imbalanced data in a certain way. Again, I'm not going deeper, but there are again mechanism to do it. That's what it is actually doing. Now, if we have not used, or basically if we have missed it, the data preparation or data understanding step, right, this aspect, then we wouldn't have used this particular balance part, right? Because we wouldn't have known also. So that's why the data understanding becomes critical, and how exactly it impacts your core modeling exercise. Max iter is where you are actually doing optimization. So essentially, I mentioned about estimating the betas, right? And we use optimization techniques like gradient descent and the likelihoods. So obviously, as you all know, that optimization needed certain steps to converge and all. So what we are saying is that your maximum iterative step is 1,000. So beyond that, if it is taking, then just kill it, right? 1,000 is a decent steps. So at the back end, essentially, all those optimizations are happening in this particular step. Then what we are doing, we are now going into the evaluation step. And for the evaluation, definitely we need to predict, right? We have to predict, and predict in that sense, one, you create a 1-0 flag based on the prediction, and then you also get the probabilities for each of these customers. So that is essentially what this particular step is doing. Now, once we have the prediction and the prediction flag and also the probability, then you can actually come up with a confusion metric. Again, the confusion metric that we discussed, right? Now, this is what the confusion metric looks like. See, it's a actual and predicted. So your 1 and 1 are basically your true positive. Your 0 and 0 are basically your true negative. Your 1 and again 1, 0 and 1 are basically your false negative, and this is a false positive. So you get, and then you can easily get all the numbers, precision, recall, F1 that we talked about. Here again, because our main objective is the recall number, so obviously the recall essentially is an important number for us. And then you go down, again the same thing. We talked about the ROC and the AOC. So if you see the area under the curve of the ROC plot, what this particular model leads to is 0.84. So this is the entire area, right, what we talked about, and 0.84 is a decent mollet as per the definition of AUC, right? So essentially, this is the way we build the model step by step, incorporating all these CRISP-DM steps one by one. And then finally, and we are assuming here that, hey, this is the best model what we have got. What we did here is basically now we say that we got the probability score. So anyone which is more than 0.7 is basically our high risk customer, right? And then, so this is basically the final outcome that, hey, you know what, these are the high risk customers what you have, and we will give the customer IDs to the business we will then take the action that how to retain those particular customers. Now, this is a very simple depiction of what we just now discussed step by step. Definitely, it's much more complicated than this, but it is just for a demo purpose. I wanted to quickly show you how all these steps comes together in a Jupyter notebook. Now, let me go back to the presentation once again, right? And I'll show you a very interesting diagram. Now, if you have to build this particular solution for Walmart, and Walmart is basically the biggest retailer in the world, it's actually every week 270 million customer visit Walmart stores. Just imagine the number, 270 million per week. Now, if I have to run this particular solution every week for this kind of a database, it doesn't happen so easily the way I showed it, right? It doesn't work that way. So this is where all the things what we discuss comes together in a scale. So if you see that these are the different data sources I talked about, that we have to have different data sources in place, right? And see how many data sources actually it takes us to. It has application data, billing data, transaction data, discount, so many things. And then we do you talked about data understanding and data cleaning. This is what we do, ETL, extract, transform, and load. So we basically transform, we clean, we do, and then finally we load the data. The modeling, if you see this particular module, the top is where we have all the modeling models, right? So we have support vector machine, we have random forest, KNN, we talked about logistic regression, gradient boosting, so many. And this is the area where actually all the databases, because we have to have a data management in place, we have to store the data, right? So that the algorithms can actually interact. So this is where we are actually storing the data. And finally, we expose the data as a data services. And then when all these models then tie back to these data services, run the model on top of it, and then it actually leads to the outcome which we just now discussed, right? The predictions, and those predictions number then gets integrated into different platform, different reports, and then the business takes the action. So it's not straightforward, or it's not only about okay, these are the 6 steps, you just write the 6 steps in a Jupyter notebook and things are done. But when you are actually solving the problem in scale, then it converts into a system, and it becomes an AI or ML system, and that is what we technically develop. So now, what are the tips for the student, right? Now, these are the 3 skill set of a data science, where again, this is basically almost 90% what all the data scientists possess. It's a combination of mathematics, statistics, programming skill, and the domain knowledge. And I'll tell you that I'll map this with each of these CRISP-DM phases, right? If you see the first step, which is business understanding, now you need to have a good domain knowledge. Now, say for example, you are building a churn model for a telecom industry and you don't understand the telecom industry. Like for example, now is 30 days a good period to say that customer is churning? That means if I am not, renewing my Airtel in 1 month, is that a good definition? Vis-a-vis the definition of churn in a retail space, in a grocery, is very different, because grocery shopping happens, we do almost every day or every week. Now, if I am actually shopping grocery from, say, Star Market, and if I haven't done this shopping for, say, 1 month or 2 months, then there's a high chances that means I'm a churn customer. But if I am say I've taken an Airtel connection and I have not renewed it, maybe a month, but or 2 months, maybe it's a high chances because obviously we need to renew it every month, right? But say in other cases, like for example, I'm buying a laptop. Now, laptop, I'm definitely not going to buy every month, right? Maybe once in 3 years, I might buy. So, what I'm trying to get to is that the definition of churn varies by domain. Grocery, there is a one definition. Telecom, there is a one definition. When you're doing a laptop, it is a different definition. When you're doing for a car industry, it's a different definition. So, until unless you have a proper domain knowledge, you will not be able to get the right business understanding. The second step is about the data understanding also. That is where also we need a good amount of domain knowledge, because how will you then tie back to the end objective? The third about data preparation is mostly this too is a heavy skill set, programming skills and math skills, because obviously you need to write the code. The concept is about the mathematics, as I mentioned it to you, outlier, variable transformation, all the things are mathematical, but you need to know how to code it and code it in scale. So the programming skill also becomes very critical. The fourth is basically your modeling. This is very heavy on mathematics skill set because you are building ML model, deep learning model, generative AI, LLMs. So it's a very heavy mathematical. You need a good mathematical foundation there. Evaluation, again, it's a pretty good mathematical skill, but at the same time, you need to have a good domain knowledge as well, because otherwise, you might just go with accuracy, but accuracy may not be the right measure for those kind of a problem, right? So you need to understand, in order to map the outcome or the goodness of it, you need to have a good domain knowledge. And finally, when you are deploying it, as you see that particular system diagram, definitely the programming skill becomes very, very important, because now you have to scale this solution for say 270 million customers coming every week. Now, if you don't have a proper good program grasp in the programming skill, you will not be able to do it, right? So essentially that summarizes that as a student, or basically as a mathematics, statistics, or econometrics students, what exactly do we need, right? So ML is an applied field. It's an applied mathematics and statistics. So I think that's where the foundation lies. Chris DM, what we talked about is nothing but it's basically how you solve problem logically. That's the framework, right? It's not like a rocket science or something which is doing very different. It's about breaking the problem and solving it step by step. The modeling or building the ML model is just one step to the pipeline. There are so many other steps. Evaluation, as I mentioned it to you, it's not only about the goodness of it, it's also about the business criteria. So it's a balance between the cost and the risk. And the deployment step is about the generalization of the entire thing. And lastly, I wanted to call it out saying that building a prototype, which I just did it in the Jupyter notebook, and taking into the production what I showed it in terms of the architecture diagram, building the system, are two very different challenges. So that's why, along with your core concepts, you need to be proficient in Python, and also Spark coding is if possible, if you really wanted to ace in the data science as a career. So that's all I have for today. I'll open up for the Q&A.
Thank you, Vishwajit, for your nice presentation, very intense presentation. And at the end, usually I ask at the end the tips for the students that you have already mentioned. Okay, let me check few questions, or those who are in the online mode in the Google Meet link and directly ask questions. But I will let me check if any questions from YouTube link. Okay, so those who are on the YouTube link are requested to type your questions so that I can directly pass it on to our speaker. So one question is there: why is the monthly bill continuous?
Yeah, it can be 100, 200, 150, 250. Anything is possible. So that's the reason.
Yeah. So this was one question. Yeah. Any other question? All the participants are requested to type your question. After that, I will share a small set of question. It will consist of 10 questions, having 4 options, but exactly one correct. That will be shared soon. But before that, there are some time we have. You can ask questions. You can write on the chat box. So that would be like, okay, sir, can you say about how do we split data into train set and the test sets? One question I got.
Yeah. So as I mentioned, right, it's a random split. Means one way is a random split. You can also split it in piecewise manner as well. There is a concept called k-fold validation. You can actually break it into k different layer and then test it on different samples. But it's the foundation is, or the fundamental is basically that your train and test set should be mutually exclusive, because otherwise then it will induce bias. And 80-20, 70-30 is a standard split, as I mentioned, but there are other process as well. I think K, if maybe I'm not using the right word, it's a K step cross validation, I guess. K fold cross validation, if I'm.
Okay. Another question is, I have the knowledge in mathematics and statistics. I also have some knowledge of email. Can you tell me what are the job opportunities and tell me roadmap about career in this field?
Yeah, I think this is the, like, it opens up your door for in the AI industry essentially, because that's the foundational skill what you need. I think you need to work on the coding part as well, because as I mentioned, at the end of the day, it's not only about building prototypes but also putting solution into the production. But other way, I think you have the right skill set for the AI industry. What you need to do is definitely maybe touch base some of the startups, some of the companies where they actually hire, where do off-campus hiring, and try your luck.
Okay, thank you. So it might be a very general question, like suppose you are at a very high end of your company and you're possessing a very high post, prestigious post. Now, suppose you want to hire some freshers. So, what are the basically things that you are looking for so that that would be a very good
Yeah.
or ideal recruitment for your company? That if you can.
Yeah, sir. I think I was anticipating this particular question, so I specifically prepared for it. So if you if you see those three circles, right? The mathematical skill set, the domain, and the programming. So what we typically do, right, when you go for campusing, because we do campusing for different institutes. So when you are going for a mathematics or statistics, like for example, when you go to ISI, right, we look for primary skill set should be mathematics, and then the secondary skill set should be the coding. These are the two parameters where we evaluate. Now, vis-a-vis, when we go to say an IIT Bombay Comp Science, right, we expect obviously things have changed right now. They are also good. Obviously, they are good mathematics as well. But programming is what we, both mathematics as well as programming, what we actually check. But when you're going to say I am Calcutta, then we typically also focus a lot on the mathematics skill set and the domain skill set, because obviously given they're coming from an MBA background, we expect a good amount of domain understanding, right? So what we do, depending on the courses, depending on the institute, we balance between these three boxes: so the coding, the mathematical skill set, and the domain.
Okay, that's great. Let me check any further question. I cannot see any further question. So it's really a great direction with Vishwajit. So I don't find anybody from online mode can directly ask questions if anyone has any question. Orpon, would you like to ask some question? Okay, so if not, then thanks Vishwajit once again for your excellent presentation. Thank you very much. And just one thing to mention, that today we might have even crossed the earlier limit of that 1,000 views within 24 hours. Let's see how many of them. So we'll able to get this exact data after closing this live session. So let's see, I will let you know exactly how many. So in the first day, on the first day, we had more than 1,000 views within 24 hours. So that was a great achievement by all of us. And that's thanks to all the speakers, all the viewers, and of course, all the persons who are helping out, helping these days. Thank you. So thank you, Vishwajit, for your nice presentation, and hope to see you in Kolkata soon.
Yes, thank you, sir. I'll let you know.
Yeah,
Bye,
sure.
everyone. Bye bye.
Bye bye. So we'll now moving forward to our next technical session, and here we'll have two presentation. Uh, One would be by someone very nice and interesting session. Thank you. I think is he here? Masim Jabal Atia, are you here? Okay, and Carl, are you here? Yeah, Carl, you are already here. Let's see, we have 5 more minutes, or maybe he may join us. Uh, Masim Jabal Atia is from Iraq, so hopefully he will join us. The next speaker would be Carl Soup from USA. So Carl is already present. Let's see. So any question or any discussion that you would like to ask, let me. In the meantime, I'll just post the questions of the data science questions. So those will be obtaining at least 50% of the marks out of 10 question. At least 5 questions would be correct for them. They'll be getting a completion certificate. Otherwise, those who have participated the workshop for significant amount of time, they will get the participation certificate. So first, I'm going to now share with you on in the YouTube the link for this question. Yeah. So this is I have already shared with you this 10 minutes time. Please fill this question paper, answer quickly so that we can have this. So the portal will be. So yeah, I have already shared with you the link of the 10 questions. So using this Google form. So please fill this form properly, and those will be getting at least 5 questions correct. Will be getting the completion certificate. Otherwise, we are also going to share soon the feedback form. Those who have been filling up this feedback form throughout last 3 days for throughout the conference. So this feedback form will be given to you periodically. Those who have filled up this form periodically will certainly get the participation certificate as well. Okay, so here we may start the session. Maybe let's see, not yet. Let's see whether he has sent any email or not. Okay, so then may I request Carl to please start. If you will come after your talk, then we may proceed to him. Yeah. Pleasure to welcome Carl Suf from US. So the title of his talk would be Color Theory, Basic Color Models 15.0, Basic Music Theory 10.0, Art 1. It's now, Carl, the session is yours.
Hey, let's see if I can get my paper.
Okay, let's see. Whether Mr. Atia, Dr. Atia, have you joined?
If he has, I'll stand by.
Okay, let's see. Yeah. So from Iraq, have you joined? Masim Jabal Atia, are you here? Okay, I think not yet.
Hello.
Yeah. So are you here?
Yes.
Can you hear me? Hello.
Okay.
Okay. Masim, can you hear us?
Yes, sir. Are you hear me?
Yeah, I can hear you. So, Carl,
Okay.
could you mind to if we can start his lecture first?
Okay.
I have no problem.
Okay,
Go.
okay, great. So, yeah, so the first speaker has arrived. So, it's my great pleasure to welcome Dr. Masim Jabal Atia from Iraq. So, Dr. Atia, the session is yours. So, you have 20 minutes of time. Please continue. Start your
Okay. Thank you so much. Okay. First of all, I would like to say thank you so much for the organizers to give me this great opportunity to meet you. Today, I like to present my presentation, which is under the title Homogeneous Mu Zeta Homo Derivations on Graded Associative Ring. Yes. 1 minute, please. Okay.
Yeah, we can hear you. Please continue.
Okay. Just
Just
some problem of my slide here.
Yeah, we can see your slide as well.
Okay. Now, in this paper, we introduce the notation of homogeneous mu zeta homo derivations on graded associative ring. We establish several structural results concerning the ideals defined by these homo derivations and investigated their algebraic properties. Illustrated examples are provided to demonstrate the applicability of and significance of the theory. In this subject, a background of this subject, we find that derivations are central maps in ring theory at the encoded differential-like behavior while preserving K-algebraic structure. They have been instrumental in the exploring ring theoretic properties, particularly these related to commutativity and structural invariance. Since their introduction, the theorem of derivations has been systematically generalized, yielding a broad and the framework that extended many classical results established for standard derivations. Similarly, the theorem of graded rings has become a gradual organizing principle in contemporary algebra. And the various mathematical contexts such as group ring, polynomial ring, tensor algebra, and cohomology theories, graded structure are naturally present, preserving gradual structural information that enhances both classification and characterization of theorems. the two theoretical development achieved vertical in unification thought. Komelenov is introduction of homogeneous derivation for graded ring, which that's happened in, or more details about the subject in references 1. The homogeneous components of graded rings are maintained in classical derivation, which ensure that both different structure and graded decomposition of underlying algebra structure are respected. As a fact, the concept of homogeneous derivation was introduced in 2018 as the following: the let omega be a G graded ring, and additive mapping lambda from omega to omega is called homogeneous derivation if lambda of xy of x y plus x of y for all xy in omega. Actually, from this derivation, it is this definition related to the derivation. Without the second one, lambda of r belong to h of omega for all r belong to h of omega, we have homogeneous derivation. Additionally, as seen, set up funding about the homogeneous derivation, he demonstrate the extensions of a non-trivial family of a non-homogeneous derivation on graded rings by extending certain important conclusions that we previously known in setting of prime or semi-prime rings to GR prime or GR semi-prime ring, including Posner's and Hurstein's theorem. Nevertheless, the author of 7 present a novel idea in graded ring known as generalized homogeneous derivation, which are a natural extension of the homogeneous derivation introduced by Komelenov references 1. The concept of generalized derivation are a subclasses that keeps element homogeneous was established by him. While in the year of 2000 came a classical definition concerning homo derivation was delivered by a Sufi in reference to where an additive mapping homo derivation concerning omega like omega to omega, where omega is a ring. In other expression, we have the following formula: lambda of xy equal lambda of x times lambda of y plus lambda of x y x lambda of y xy element in omega ring. This where we add this just this term, we have homogeneous we have homo derivation. Now the fact we have every homogeneous derivation is a derivation. However, the converse statement is not true generally, as there exist derivations that are not homogeneous. Now, in this slide, we find the Bernoulli's here gamma, here omega represent an associative ring with the center Z of omega, and G is an abelian group with identity element E for omega for 2 elements xy in omega. We write the commutator this for Lie product xy take away yx and x circle y to the anti-commutator for the Jordan product xy plus yx. For an empty subset S of omega, we write C sub omega of x of C equal this set for centralizer of S. A ring omega is G graded if there exists a family omega sub G, G in capital G, of additive subgroup of G of this subgroup, omega with addition, such that omega equal this formula, direct sum of G sub G, G small and G capital, and also omega sub G, omega sub times omega sub G, omega sub H subset from omega sub GH for every GH belong to G. The additive subgroup omega sub G is called the homogeneous components of G. The set of H of omega, right by this way, is the set of homogeneous elements of the ring omega. Here also, we need to the definition of the right and left ideal of a graded ring. Then delta is said to be a graded right or respect left ideal if delta equal direct sum G sub G belong to G, delta of sub G, where delta of G equal delta intersection omega G, omega sub G for all G in G, that is for X. Also here I wrote this formula, this relation between X and the summation. A graded ring is said to be G prime, GR sim prime, if A omega P equals 0 implies A equals 0 or B equals 0. If this for GR prime, GR sim prime, A omega A implies A equals 0, where A and B belong to the set of homogeneous, where A and B homogeneous element of omega. Moreover, a graded ring G is G prime, GR semi prime ring if the intersection of all the G are prime ideals is 0. As shown in the group ring, there exists GR prime, GR semi prime ring that are not prime, not semi prime. Also, for or more details, we refer to the references 9 if you need more example and more facts concerning the relation between GR prime, GR semi prime with prime and semi prime ring. Moreover, information above the previous concept that omega is a prime, if satisfy this, also if R prime here implies A equal 0. All prime rings are semi-prime rings. This is general, not specific about the graded ring. And here A and B is not homogeneous element, normal element of a ring. Here in relation, all prime ring are semi-prime ring, but this is not true otherwise in case of AB. An element AB equal PA, P omega is commutative, here commutative ring. Also, we have another principles or another concept is homogeneous, like this GR, a graded ideal of R is weakly scaled weakly GR semi-prime if for any homogeneous element A such that and not equal to greater than or equal 1, we have this relation. Also, we have the following relation between GR prime implies GR semi-prime implies to weakly GR semi-prime. Little h of omega is the graded ring, graded algebra, and omega homogeneous element. The centralizer of all homogeneous element in h of omega is the set by this formula for all homogeneous element. In other words, lambda belongs to the centralizer if it is commute with every homogeneous element in the ring. Here we find an element A, an element of omega is called weak GR0 divisor if there exists a non-zero homogeneous element such that AP equals 0 or BA equals 0. We have also, this is definition of derivation. I spoke about that in the first slide. Also here, when we have the derivation is an derivation overall R in omega during the commutator by this way, the commutator lambda of A with A power N belongs to Z of omega. This inform that the here misprint here lambda that form an centralizer covering of a ring omega. While when K belong to Z, then lambda is central mapping over omega. When n is not equal 0 is an integer. Indeed, the reader can say a ring has n Tauschen free. This here an n Tauschen free, and here is not equal 0 times A yields A equal 0. In this slide, we start my main result definition. Assume omega B is a GR graded ring in additive mapping lambda from omega to omega is called homogeneous mu zeta homoderivation if lambda of xy equal lambda of x, lambda of y plus lambda of x mu y plus zeta of x lambda of y for all xy elements in omega. Zeta and mu are automorphism mapping of lambda. Delta of this is the second question. Lambda of R belong to H of omega for all R belong to H of omega are here element homogeneous element. The following example expression the previous definition represents in the main definition. Here I take the omega by this formula and selected for elements Z0, Z1, Z2, omega sub 0, omega 1, 2, and 3, and define the lambda by this formula, mu alpha beta alpha equal alpha beta, and zeta by this zeta of alpha beta alpha equal alpha beta 0 alpha. This definition, this example has many details, and it's difficult write all details in this slide. In the full paper, you will find all the details, and we will find the proof that it is really homogeneous mu zeta homoderivation. Remark: every homogeneous mu zeta homoderivation is mu zeta homoderivations. However, the converse statement is not true, as there exist mu zeta homoderivation that are not homogeneous. This can be demonstrated by the following example. This also following example. Another example. This example explains the relation between homogeneous mu zeta homoderivation and mu zeta homoderivation. In proposition 3.1, let omega be GR prime and delta a non-graded left ideal of omega if lambda is a non-zero homogeneous mu zeta homoderivation, then it is a restriction on delta, is a non-zero. When a lambda is a homogeneous mu zeta homoderivation of omega in the previous proposition 3.1, immediately we conclude the following corollary. Corollary 3.2, let omega be a GR prime ring and delta a non-zero graded left ideal of omega if lambda is a homogeneous mu zeta homoderivation, then delta of omega equals 0. Theorem 3.3, let omega be a 2 free GR prime ring if lambda is a homogeneous mu zeta homoderivation and W belong to H of omega such that the bracket W with lambda of x belongs to Z of omega for all x element in GR prime ring, then lambda equals 0 or omega belong to C of lambda of W. Corollary 4, let lambda be a 2000 free GR prime ring if lambda also her omega zeta homoderivation such that the bracket, the sum previous bracket belong to center of omega, then W is central like homogeneous element. Theorem 5, 3.5, consider a GR semi-prime ring omega that is a 2000 free, let delta be ideal of omega and assume that omega has no non-zero divisor. Suppose that mu and omega are automorphism of omega. If lambda is a homogeneous mu zeta homoderivation satisfy lambda power 2 of v equals 0, v element of omega, then delta acts as a weakly GR semi-prime ideal over mu of omega. Omega has a weak GR0 divisor. Delta is a 0 homogeneous zeta mu zeta homoderivation for homogeneous element over lambda. Corollary 3.6, assume omega is GR graded ring without GR0 divisor and delta is ideal over omega where lambda has a homogeneous mu zeta homoderivation. With this condition, then lambda of omega equals 0 where mu and zeta act as automorphism mapping of omega. Theorem 7, assume a GR semi-prime ring with a 2000 free, suppose mu and zeta are automorphism mapping over omega, let lambda be homogeneous, mu zeta homogeneous, satisfy this identity bracket lambda of v1 with lambda of v2 equals 0, then lambda is centralizer of all homogeneous element of H of G where v1, v2 elements of the ring. And the corollary 3 point, we can derive the next corollary. Assume a ring omega is a 2000 free GR semi-prime ring and delta is an ideal of omega. Suppose mu and zeta act as automorphism mapping over omega and
you have 2 minutes.
Yes, that's this one.
Yeah.
When omega admits to the lambda satisfy this condition, lambda of x circle lambda of y, where xy and omega, then we have the following result is. Yes. Finally, I close my representation by the list of the references which used during my work. This one. I hope it's a good opportunity for anyone to increase his information about the subject. Thank you so much for all.
Thank you very much. Let me check. Any question or comments if you have, those who are in online mode or those who are in YouTube? Okay, so no question that I can find. So let's thanks Dr. Atia for his nice presentation. Thank you.
Thank you so much for you. Thank you so much for all.
Okay, thank you very much.
Okay,
Stay with us. Now may I request our next speaker, Carl Soaps from USA, to have your presentation, please. The session is yours now. Yeah.
Okay.
Yeah, Carl, could you please? Yeah, so that's correct. Yeah, thank you.
Can you see my screen?
Yeah, so could you please cut the portion that is coming, the screen? Screen is, a small screen is coming on your presentation. So if you just cut the your screen, not that one, or maybe, could you please, yeah, this one. Yeah.
You need me to do what?
You just cross it because it's overlapping with your presentation. So yeah, just on the right, you have a cross sign. Yeah, cut it. Yeah, that's fine.
Okay.
Thank you.
And I need to get this centered. Okay, you can hear me and you can see my presentation.
Yeah, your sound is clear and your presentation is visible. Thank you.
Okay, and I'm ready to go. All right. The title of my paper is Color Theory, Basic Color Models 15, Basic Music Theory 10, Earth equals 1. So this is a series of thoughts that I've put together, and the tracking of the numbers is where I'm at in this research. So what I'm going to do, I don't know if it's going to work, but I want to explain what my theories are based on, and that Earth equals 1 was a concept that developed with a paper that I did last year, and that it's proposing that time is a spectrum versus a single point or 1 second, in that 1 second is actually just a particular vibration within that entire spectrum. So what I'm going to try to do is go through my abstract, and then I'm going to introduce you to some of my figures that I have, so that you'll have some kind of reference to go by in terms of what I'm talking about, and we'll see how that works out. Okay, the universe is defined by what we see, detect, infer, or deduce per Earth equals 1, white light reference. Therefore, the universe is defined by what we see temporally per the Earth equals 1 temporal white light reference. Relativity explains the very large things in the universe. Quantum mechanics explains the very small things in the universe. This paper is a relativistic approach to the universe. The concept of Earth equals 1 reference can be foreign to our way of thinking. This research addresses the concept of Earth equals one, white light reference, gravitational reference, temporal reference, etc. The Earth equals one reference is regarding the international standard of 1 second per timekeeping. Per the international standard, 9,192,630 vibrations of a cesium atom equals 1 second. Therefore, the vibrational rate is actually a frequency equals to 1 second. This vibrational rate is used in atomic clocks as a vibrational rate. A Jacob's ladder correlation can be identified for time within the visible light spectrum. This is where a specific vibration within the visible light spectrum harmonic or color octave is associated with Earth equals one's temporal reference for 1 second. Then the concept is expanded to time itself, a temporal spectrum, in the crystalline balanced system of systems, multidimensional fabric of space in its subspaces, that of 4D temporal space, 4D electromagnetic space, and 4D spatial space. Now this goes not so much hand in hand with Einstein's concept of the fabric of space or space-time. It's my version of visualizing the fabric of space in terms of it being constructed of subspaces that are potentials that make up what we call the fabric of space, and that these subspaces balance to zero based on what I have developed in terms of color theory. So some of the models that I'm going to introduce you to so that you'll have a working idea of what I'm talking about. This is the model that I came up with to represent the fabric of space. And this is constructed on an equilateral triangle, then expanding that equilateral triangle to being representative of a tetrahedron. And the larger tetrahedron is made up of 3 smaller tetrahedrons for the base, with a tetrahedron balanced on top of those 3 lower tetrahedrons. And then you flip it upside down to get the plus and minus, and that these are representing my subspaces that make up the fabric of space, and that I'm going with the associated geometry. And I'm going to talk about music theory and that how the circle of fifths is developed. I'm not going to go into a lot of details, but just to show that there's a reference to time, in that when you develop the circle of fifths, that you initially develop it in terms of primary tone F. And once you establish the positions of the 12 semitones that are associated with it, and I've associated color with those 12 semitones, and that you have your 6 primary colors and you have 6 interfaces between those colors, which relate to the numbers on the face of a clock. And so instead of trying to reference a particular color or a particular semitone, I'll probably just reference the clocking that's associated with it. The other model is this one, where once you've established your circle of fifths, you can start with any of the tones, and that will give you the key that you're working with. So establishing the circle of fifths, it's in the key of F. And so you go from F to F. And if you start with G, you go from G to G, and it's in the key of G. Displaying the circle of fifths and displaying the color that's associated with it, it's displayed like the numbers on the face of a clock. And that's what this is demonstrating. And I'll be working with the letters in this inner circle here. And the other thing I wanted to point out is that the octave and therefore the harmonics that I've associated with this, which is identified within my harmonic distribution, which is Jacob's ladder, begins and ends at the 7 o'clock position, D flat. And that what I want to point out here is that when you look at this, think in terms of the length of a string, and that from D flat around this circle is a rising octave. I'm going upwards. And this is like a spiral staircase. And just in the same sense, I can go up an octave going clockwise, and I can go down an octave going counterclockwise. Another tone that I'll be dealing with is F. And when you start F, the octave has already started, and you go 20 degrees, or in a sense 4 hours to F, and the string for F is shorter, and you have to jump to the next higher string in order to complete your octave in F. And that's basically how it works with that. So the consideration that we have to make is that the differences of what's going on has to do with a vibrational rate, and that vibrational rate will give you a different, in a sense, tone or flavor to the vibration that you hear. Now, my research has been with color, so I developed a color model, and I come up with what I call color math, and it starts with the concept that a balanced equation will allow you to identify the primary colors of a particular group: red, green, or blue, cyan, magenta, and yellow. So the starting true statement is red plus green equals blue. And that with that equation, with red equal 1, green equals 2, then blue equals 3. And working with that concept, I developed a harmonic distribution called Jacob's ladder, which allowed me to move my color model throughout the entire electromagnetic spectrum. And at the lower end of the electromagnetic spectrum, those vibrations are also found in the range of sound. And to test that correlation, that I made a connection to music theory. And so I found out that my harmonics and subharmonics of my work also related to the rising and lowering harmonics within music theory. And I decided that, okay, can I apply all of this to something that I don't know, which is time? So we have time, and we know what time is, but time for us is timekeeping, and it's our method of tracking the passage of time. And with space-time, time is one-dimensional. And what I'm proposing is that time is four-dimensional at least, and that it's a potential, one of the subspaces of the multidimensional fabric of space, and that my goal is to show that when temporal space and electromagnetic space and spatial space are combined together, they equal zero. And the reason that we haven't been able to find or detect a medium, and that's what the crystalline multidimensional fabric of space is. I see it as being a medium, and that space isn't just a empty vacuum sitting out there. So the subjects addressed in this paper are approached as assumptions. The assumptions are based on previous basic color theory research. An attempt is made to contrast versus critique an existing theory with that of the assumptions of this research. This basic research was made possible by standing on the shoulders of the giants that came before us. Curved MD fabric of space, where no time dilation is experienced, defines the temporal frequency of Earth equals 1. Any temporal frequency above or below Earth equals 1 is time dilation. Time dilation drives redshift and blue shift of white light. When approaching the speed of light, white light becomes redshifted. Temporal wavelengths become longer. When approaching a black hole, white light is blue shifted. Temporal wavelengths become shorter. The greater white light is blue shifted, the faster time cycles. This concept is based on crystalline curved MD fabric of space and temporal slope. The more massive an object is, the more the crystalline MD fabric of space is curved. This ties in with the Hubble constant in terms of what's going on. The Hubble constant is how fast objects in space are moving away from each other, which is in contrast with what they're finding with the cosmic microwave background, and they're getting different answers, and that results in what they call the Hubble tension. But what the concept that I'm trying to present is that the fabric of space and things in space are different entities, and that the fabric of space is doing its thing, and objects in space are doing possibly something different. So 1 second is the key of is in the key of D flat in its near semitone D flat, and open issue is whether or not time as we experience it is a single frequency or a temporal white light to speak of. So when you combine red, green, and blue, that it makes white or white light source. And what I'm doing to develop this concept is I'm saying that temporal space has the same conditions or the same characteristics of electromagnetic space. And that gives me a way in which I can approach the concept of temporal space as it being a temporal spectrum. This research, the lower limit for the visible light color harmonic was calculated at about 432 terahertz and goes as high as almost 700 terahertz. And so what I'm developing is that from the cesium atom vibrations that's used to define 1 second, that I'm using the harmonic distribution of Jacob's ladder to increase the harmonic rate of that vibration. And so that vibration is defined by phi, big phi, and taking that cesium atom vibration as a frequency and multiplying it, or putting it another way, this is a tone. And I'm going to raise that tone 23 octaves. And that gives me a value within the visible light spectrum. And therefore, from that reference, that I can have a visible light reference for 1 second, which again fits in with the concept of Earth equals 1, and that frequency will tell us that, okay, values above or below that value is time dilation. And what I'm also needing to figure out is that this value is the lower limit of that octave, that the value, the range of frequencies that's associated with that octave. And to get the upper limit, that you would raise this value to the 24th power, and the upper limit value minus lower limit value gives you the total range for that particular octave. And so we're working with the visible light octave in terms of what the total value is going to be. I'll show you in a little bit what that is talking about. And since we're talking time, in the calculations that we use typically is for the electromagnetic spectrum, that we have to consider the clocking or the differences between the electromagnetic spectrum and the temporal spectrum. And so the electromagnetic spectrum is in the key of F, and so the vibration will stay the same, but the clocking will move around to the clocking for temporal space. And that's the significance of the length of the string where it comes in. So the orientation of this particular geometry shows that temporal space and EM space is 120 degrees out of phase with one another. And to get this clocked correctly, I had to figure out, okay, where is my zeros, and where, how do I get this oriented so that I can, talk about what's going on, what's where. And I'm at such a fundamental level with this that I'm ending up with more questions than answers that I've come up with. And the other thing I wanted to express is that my disclaimer, I'm just following the math. I'm not promoting any philosophical beliefs, but I am finding it curious that when you look at some of the ancient teachings or whatever, that they talk about the hexagram being a representation of the cosmos, and that the three-dimensional version of this is actually a star tetrahedron. Metatron's cube is believed to have or contain all of the regular solids. And one of the questions that I've come up with is that in the cosmos, where does the information come from for things to form, develop, whether it's an atom or whether it's a planet or whether it's a solar system or a galaxy? And where does the energy come from? And, I just kept coming up with nothing. And if there is a fabric of space with a crystalline structure that it opens up the possibility of there being a source of power and a source of information to some extent. And this table is just a short version of just what I've explained and how I came up with my values. And with that, also when I'm talking about tones and vibrations, that there's another music concept that's overtones and undertones. So you don't have just that frequency like with a musical instrument. That a characteristic of a musical instrument is that when it plays a particular tone, that it also vibrates in additional tones, either above or below the tone that you're playing. And if the universe is defined by what we can see, detect, infer, and or deduce, then time is defined by what we can see, detect, infer, and or deduce temporally. Again, coming back to this table, the question that I've been asking myself is again, with the age of the universe, and if the universe started, say, with the Big Bang, is what we're seeing, is it representative of chaos versus order? And if it's order, music theory is order. And if the universe is following music theory and you're able to hear music when they sonify a digital image from space, it just gets into what does it mean? How do we, I guess, figure out what the universe is doing? And so figure 301 demonstrates the theoretical correlation of the circle of fifths to the visible light spectrum. So this is figure 301. If everything vibrates, and when you combine red, green, and blue, it results in white light. White light has no frequency, and that's the concept that I'm playing with in terms of you having subspaces that balance to zero. It's a zero that's above the x-axis in a sense, so that when you have white light, you can use a prism to sort that white light, and you get the 6 primary colors plus orange, and that if you pass that white light through another prism, that it reverts to its white light status. So if this concept is sustainable, that I'm proposing there's additional dimensions to space. This particular model represents the YZ plane. The x-axis is coming up through the center, which is Jacob's ladder, and that you have the YC, the YZ magnetic field or current. You have the XY electric field or potential. This is a spiral staircase, the way it's representing things. So it involves torque. So you also have color harmonics, color octaves, etc. And using Planck's equation, where energy times the Planck constant, energy is equal to Planck's constant times frequency. So you get energy from out of the system. And so what I'm looking at here is having to come up with, okay, making the assumption where 1 second is, it happens a little bit before the 7 o'clock position. But I'm able to use the concept of color to determine what the lower limit is, and I can calculate what the upper limit is, and the upper limit minus lower limit. I can divide that by 3 and determine the length of one leg of an equilateral triangle. And I can apply that concept and figure out what the values for the other two legs should be. And what I'm needing to prove or to show in some way that this concept is valid, and that one of the things that I'll point out for this particular figure is that the total range value that I'm using is for F. The concept that started with this is a gift from Pythagoras, with him figuring out the circle of fifths, and the 0 is at the 11 o'clock position, and primary red or semitone C is always at the top. And from that, doing the calculations that I worked with, it showed that from 0 to the 11 o'clock position was 120 degrees, and I worked with that. So again, this is showing where I'm thinking or trying to figure out, okay, where am I going to go with this, and how am I going to demonstrate what I need to do. And these are the values, but it's easier to see when I just show you that starting with 0, if I go to the 11 o'clock position and just associate an arbitrary number to 120 degrees, that if the different subspaces are oriented 120 degrees from each other, then it puts temporal space at 240 degrees. And that's where working out the combining of vectors ended up with 5 when I combined these two vectors. And assuming, we're here. Yeah, I used 0 because 180 didn't work. So anyway, this gives me my equilateral triangle. And another concept that I wanted to explore here was that instead of using 5, if I use a vibration instead of just, a magnitude, and doing that, I still should get the same value that I had used here. And the question that I had with this is whether or not this describes color tonally. So I would have 3 different versions of this vibration, but they would have different tones. So getting into applying these concepts to my subspaces. So temporal space is at the 7 o'clock position. EM space is at the 11 o'clock position. And now I've established that spatial space is at 0 or along the x-axis, and showing that EM space and temporal space are similar in a sense, but they're 120 degrees out of phase with one another. And what follows from here is just me applying the color concepts to establish my modeling, and I'm starting off with red plus green equals blue, and this is my color math that I'm using, and that when you combine all three in this balanced equation, you end up with 0 is equal to 0, or white light source, which I'm applying the same concept to my three subspaces, ending up with 0, and that it talks about a balanced system of systems, multidimensional fabric of space. So I step through and look at EM space, and EM space is aligned with electromagnetic space. But what this also points out is that it's all electromagnetic space, and that time is just in a different key than electromagnetic space, and spatial space is just a different key than the other two. And so this is a spiral staircase, and so you could kind of picture it as a cylinder, and with time being involved, I'm not sure where our time begins, where our time ends in regards to the current moment. And so when we look at a black hole and we talk about, we get no vibrations from that black hole, and it's something we can't define. But again, if it's a vanishing point where it's pushed beyond our current moment, a black hole isn't like the end of time. It's just the end of our interface with that particular space or that area. And again, I'm just going through, and spatial space. What is spatial space in terms of a potential? And again, that's something I'm still needing to work on. It just has me really confused as to, is this something that talks about dimensions or size, and how does that change if we were to approach a black hole, or if we were to approach the speed of light? And this was just a little something I did on just the orientation of things. But in basic music theory, when three or more notes are played simultaneously, it's called a chord. The basic color theory identified a red, green, and blue relationship between 4D temporal space, 4D EM space, 4D spatial space. The concept of color, harmonics, and color octaves is that of a spiral staircase. Going 360 degrees clockwise raises the pitch by a color harmonic or color octave, as defined by phi to the x power. Going 360 degrees clockwise lowers the pitch by a color harmonic or color octave, as defined by little phi raised to an exponential value. This paper argues that the crystalline MD fabric of space is a reactive medium or venue where objects and events happen. Mass, E equals mc squared, is assumed to be a separate entity from the crystalline balanced system of systems, MD fabric of space, which I will probably in the future just refer to it as being ether. But the two entities interact. If the universe is defined by what we can see, detect, and infer, and or deduce per and Earth equals 1 light reference, then time can be defined by what we can see, detect, infer, and or deduce per and Earth equals 1 temporal white light reference. The more we learn about this system of systems, the more we learn about the universe as a whole. The whole is greater than the sum of its of the parts. Aristotle. Thank you.
Thank you, Carl, for your timely presentation, and it's a time for question answer. If anyone from the online mode, please unmute yourself, and if you have any questions, please ask. Let me check if any questions are there. Yeah, so there are many comments. So one comment, the whole is greater than the sum of the part. Okay, it's just a comment, I guess. Very informative presentation. There are, let's see. Okay, so one, it might be a comment. Length construction is the phenomena that a moving object's length is measured to be the shorter than its proper length, which is the length as measured in the object's own wrist frame. So I think they are not questions, they are mostly comments. I cannot see any questions. Okay.
Okay.
So thank you so much for joining with us. And so please be tuned. And thank you, Carl.
Thank you.
Okay. Yeah, now you have the duty to be given to you. Now it's my great pleasure to welcome Carl again, but in a different capacity. He will now be chairing the session, and I can see that the next speaker is already amongst us. Bivas is here, and I think the other speaker, Rohit, will be joining soon. Okay, both Rohit and Bivas are already amongst us. So now, Carl, may I now request you to please chair this session? Session is yours. Both the speakers are present here.
Okay. Thank you. So is Deepas Adhikari ready to go?
Yeah, sure. Can you hear me?
Yes, I can.
Yeah, sure. I'm ready.
Okay, I can see your screen.
Okay.
I can see your presentation. Looks like you're good to go.
Oh,
So
thank
whenever
you.
you're ready, sir.
Yeah. Okay. Yeah. So before I begin my talk, I would like to share a few personal words. Okay. Is my slide going? Okay. Let me. Is it moving forward?
Yeah, it's moving forward.
Okay.
Okay. Yeah. So before beginning my talk, I'd like to share a few personal words. I am a proud student of Professor Mahima Ranjan Adhikari. And during my master's studies at Ballygunge Science College, he taught us a course on module theory and its applications. Beyond the classroom, I was fortunate to share a cordial and enduring academic relationship with him. On many occasions, I sought his guidance, not only on my studies, but also on broader academic and professional matters. And he was always generous with his time, insights, and advice. And I'd like to congratulate Abhishek for continuing this remarkable academic legacy. And I sincerely thank him for giving me the opportunity to speak at this conference. The title of my talk is Implementing Permutations on Quantum Devices. And I'm currently a principal researcher at Fujitsu Research of America, We are located in Santa Clara, California. And this material here is based on this recently published article. However, the focus in this talk would be only on implementing permutations on a quantum register rather than random sampling. But the content is a part of this paper. And here I'll go. So in this talk, I'll mainly focus on the combinatorial framework for expressing polynomials as a product of adjacent transpositions. And I'll also discuss the quantum context of why we want to express this as a product of adjacent transpositions. And we also discussed the classical algorithm, which is known as Steno-Johnson-Trotter algorithm. Yeah, and then I'll talk about how to implement a permutation on a quantum register, and I'll also discuss a new graph representation of symmetric groups. So a fundamental problem in mathematics is like in group theory, like given a group and a set of generators of the group, how do we express an element of the group as a product of its generators? So here the context is that the group is the symmetric group, and the elements of the symmetric group are called permutations. And the generating set here is there can be many generating sets of a group. Here, for the case of symmetric group, we are considering the generating set as the set of adjacent transpositions. And the group is defined on this underlying set, labeled as the elements, n elements, labeled as 0, 1, n minus 1. And there are many standard notations to denote a permutation. And here we consider these two notations. This is called an array notation, which is bracket parenthesis. So here it means, like when I write this, it means like pi is the permutation. So pi of j is xj. So for example, here if n is 4, so we have 0, 1, 2, 3, and if I write it this way, bracket, it means 0 goes to 0, 1 goes to 2, 2 goes to 3, 3 goes to 1. And if we write this notation, which is known as cycle notation, so here pi of x jl should be x jl plus 1. So here 0 goes to 2, 2 goes to 3, 3 goes to 1. So ultimately, this notation, like first parenthesis notation, is basically this bracket notation. So these are the two notations that we'll be using, and the definition, like it will be clear from the context. Yeah, so then the question is, what is the quantum context here? This is a fundamental group theory problem. So, and why do you want to implement a permutation on a quantum register? So this can also be thought of as compilation problem for permutation. So when I say, so this is quantum compilation, meaning if we have a permutation operation, then how do you implement it in a quantum computer, in particular digital quantum computer? So yeah, so the connection of this problem with linear algebra is basically if you have a vector space or any field. So here mainly we focus on the field of complex numbers. So if V is a vector space of dimension d, and suppose this is the ordered basis of the vector space, then any unit vector from the vector space always can be written as this. And we are assuming that it is unit, so the norm is 1. Then the permutation, if we take a permutation from SD, then if we apply this permutation on this vector, so we are treating this permutation as a permutation matrix, so it's a transformation. So it will act on V element-wise, entry-wise, so it will act on every basis element of the given basis, and which is equivalent to write this way. So basically, it interchanges the combination of the coefficients of the vector B. So you get a new vector B, but the coefficients are swapped in between, depending on what permutation you choose. Because basically permuting the coefficients of the vector. Now, what is this connection to quantum? So let me just give a brief review about quantum computation. So like classical computation, we call it bits. So anything we represent in a digital classical computer, a computer is basically expressed as a string of zeros and ones, which are called bits. So in a memory, so basically we have, depending on the memory size, we'll have a sequence of zeros and ones. So in quantum computer, instead of bits, we have qubits. And instead of 0, 1, we have two vectors, 0 and 1, which will use the notation ket 0 and ket 1. So basically, any qubit is lying in a two-dimensional complex Hilbert space. So basically, it's lying in C square. So, and it is a unit vector. So the basis, so there are two basis elements. So there can be two orthogonal qubits, one in the, let's say, the x direction and one is in the y direction, but it is in the complex space. So there are basically 4 real parameters, but this qubit, which is a linear combination of 0 and 1, so since it is a unit vector, so there will be only 3 real parameters, and we can see, or we can represent a qubit as a point on the sphere. However, if we consider these 2 angle parameters, then we need only 2 parameters to write any qubit in this world. So basically, a qubit is nothing but this blue qubit, like the 0, ket 0, we call it ket 0. So this is basically the first basis element. And so in the x direction, you can think of, and 1 is the y-axis, the other orthogonal basis element. And anything else is basically on the sphere. So this is what a qubit is. And now, if we consider an n-qubit system, okay, then basically, so n-qubit quantum state is a vector which lies in this vector space. So it's c squared to the power n. So it is basically n times Kronecker product or tensor product of the vector space c squared. So it has dimension 2 to the power n. So it's exponential dimension. So any n-qubit quantum state, so it's basically a unit vector in this vector space. And any evolution of a qubit, meaning, so you have to change that. So whatever you want to encode, so some message you have to encode in an n-qubit quantum state, meaning you have to encode that information in the amplitudes of the basis elements when you write or when you express the state as a linear combination of the standard basis elements of c squared to the power n. So yeah, you need to encode those information inside those probability amplitudes. And the evolution of a quantum state is described by a unitary matrix. So basically, any quantum evolution is modeled by a unitary matrix. So if we have a state, let's say an n-qubit state psi, get psi, then we denote it. This is called a quantum circuit representation. So this is which we call a get. So U will be applied on psi. So psi is a vector, U is a matrix. So U times psi would be the outcome. So this is a typically circuit representation of a quantum operation. And permutation matrix is basically a unitary matrix. So what we want to do here is, if U is the permutation matrix, so the question is in a quantum register. A quantum register means like you have n qubits somehow arranged. Okay, so each of these horizontal lines represents a qubit. So there are n such lines, or wires, you could call it. And then the question is, how do we implement a permutation matrix here? And yeah, so the idea here is in this talk that what we worked on is basically how to express the permutation matrix as a product of these adjacent transpositions. And then the question is, when I express this, then each adjacent transposition, how do we implement? And if we know how to implement a transposition, in particular adjacent transposition, then we will take a sequence of that, and then how we'll implement a permutation matrix. So, for example, let's say, here there are some elementary gates. In fact, these are the 3 elementary gates which are enough to implement a permutation matrix in a quantum register. So, for example, this is called X gate, so which corresponds to this permutation matrix. So, this is a standard gate. Like if you have a quantum computer, you know how to implement this experimentally. So, what does this gate do? So, it will take 0 to 1, 1 to 0. That's 0 meaning the gate 0, meaning it will take x-axis to y-axis and y-axis to x-axis. And mathematically, it is just this flip permutation matrix of order 2, because a qubit, remember that it's a vector of dimension 2. So yeah, and then we have, this is called, or sometimes this X gate is also called NOT gate. And C here stands for controlled NOT gate. So here, this is the gate on a 2-qubit system. So the first qubit is here, second qubit here, and we are writing in here is a black dot, the dark dot. So here it means it is the controlling qubit for the operation. And this is the target. So here it means when this qubit is 1, then this X gate will be applied on this. So depending on whatever Q0 and Q1, so this is just the direct sum of like the modulo 2 operation for Q0 and Q1. So this is the output. So if whatever input it is, like if you look at it, so if you want to understand a transformation, we have to see how does it behave, what are the outputs of that transformation on the basis elements, right? So and basis elements here are 0 and 1. So here it will be 0, 0, 0, 1, 1, 0, and 1, 1. Based on that, you will see the outcomes here. And then for any 2-qubit quantum state, you can find out what is the output based on the output of this transformation on the basis element. So it is very clear how this acts. So so mathematically, this gate, this control NOT gate, is basically a permutation which looks like this for a 2-qubit gate, and it is a 2-qubit gate operation. And if we increase the number of gates, for example, 3-qubit Toffoli gate, this can be extended for any number of qubits. So here I choose to give you an example on 3-qubit. So these wires, the horizontal lines, they represent the qubits, and here this gate, here the X gate basically is applied when this is 1, the first qubit 1, and second qubit is also 1. So meaning these 2 qubits, first 2 qubits, they act as the control qubits, and the third one is the target qubit. And Toffoli gate, so because it's a 3-qubit gate, so the dimension is 2 to the power 3, which is 8. So this 8 by 8 matrix, which represents a permutation matrix. And here, this is how it looks like. You can extend it. Here, basically, the principle is the same. So, for example, an n-qubit Toffoli gate is basically you have to consider the control qubits as the first n-1 qubits, and the X gate will be applied on the last one. So these are 3 fundamental permutation matrices, and the corresponding gates are NOT, C0, and some qubit Toffoli gate. And we'll see that any permutation can be implemented using these 3 gates only. So, okay, now the question is where to use it. There are many applications that you can find in standard textbooks or recent papers. Why do we need to implement a permutation matrix on a quantum register? So one application is this. This is not done by us. So I'm talking about this paper. So this is known as a quantum permutation pad. So here what you do is, if you want to hide information, or you want to what is called encrypt some information. So information is encoded in the probability amplitudes of the vector, which correspond to the quantum state. And when we apply the permutation matrix, so the coefficients are swapped. So that is how the message is encrypted. And due to the huge dimensional space, so it has dimension factorial of 2 to the power n for an n-qubit system. So these many permutations are there. So basically, because when you have an n-qubit quantum state, so this is lying in 2 to the power n dimensional vector. So you have the probability amplitude, so 2 to the power n, and then you are applying a permutation. How many permutations possible? Because here the number of underlying state is 2 to the power n size, so it is 2 to the power n factorial. So it's a huge set, and we can exploit possibly this for quantum encryption. So this is why you need the quantum permutation pad, and this is where you need to implement a permutation matrix on a quantum register. So this picture is taken from this paper. This paper is open access paper, so you can go ahead and read it. Okay, now let us discuss the algorithm, which, like, how to generate, how to write, how to express a permutation as a product of adjacent transpositions. Oh, by the way, the adjacent transpositions meaning basically JJ plus 1. So this is a 2 cycle. J goes to J plus 1, and everything remains the same. So yeah, for example, if n equal to 4, let's say that is 1, 2. That means 1 goes to 2, 2 goes to 1, 0 goes to 0, 3 goes to 3. Okay, now, so this is one of the nicest algorithms how to generate all permutations, which is also a very difficult task, you see, because if it is n, so if the underlying set has size n, but we have 2 to the power n number of permutations, right? So the question is, classically, how do you generate all the permutations? So this is expensive, but this is one of the easiest way to do that. So when you write the permutation as array, so n equal to 1, so you have only 1 permutation. N equal to 2, you have 2 permutations. So what you do is you take this 0 and then include 1 in the left and right of this 0. So that's how you get 2 permutations. And then if you want to do it for n equal to 3, so this is a recursive framework. N equal to 3, so you pick each of this for n equal to 2. First take 2, then you place 2 consecutively by changing its position from right to left. So you start with this one, then first take 2, then put 2 in the middle, also make a shift to the left side, and then again one left side shift, and that will give you these 3 permutations. And then for this, again include 2, and then gradually move it towards the left, and that's how you get all the permutations. We have 6 permutations here. Now for n equal to 4, the factorial 4, which is 24 permutations. So what you do is that from each of this you start, and then include this new symbol, which is 3, and then again move it towards the left, and do it for each of this. So that's how you get all the permutations for n equal to 4. So this is that very simple algorithm. So this is a work of 3 people, and this is known as this Steinhaus, Johnson, and Trotter algorithm. This is how you can generate. But we observe a nice thing. It was also observed before, but we formulated it in a different way. So in a combinatorial way. So what you see first is that this one, let's say we consider n equal to 2. So we have this 0, 1, and 1, 0. And remember that we want to express these permutations as product of adjacent transpositions like this. So depending on what k is, sk is, we have this many k such adjacent transpositions. So for k equal to 2, let's say 0, 1 is identity, because 0 will go to 0, 1 will go to 1. And 1, 0 here, 0 goes to 1, 1 goes to 0. So this is S0, basically. Okay. So these are the only 2 permutations. For 3, we see that the first one is identity, second one is S1, third one is S1 S0, fourth one is again S0, not again S0, first time S0, and this one is S0 S1, and then S0 S1 S0. So basically, we can derive a general formula like this. So for any so Sn is generated from Sn minus 1. So how do you do that? So suppose we have Sn minus 1. Now we want to look at how do we generate Sn. So then, okay, so how Sn minus 1 is generated for Sn minus 2, let's say. So you introduce a new symbol, which is n minus 1. And this was the primary thing which was there. Some jth permutation of Sn minus 2. First, you include the new symbol at the extreme right. So that will be same as this one before. And then when you replace, make a shift, make a move towards the left, let's say at this position, at the kth position, this k is important, at the kth position, then you see that this new permutation, which is in now Sn minus 1, would be this. So wherever you started from, this one, so this is same as this one. So where you started from, and then it's a product of starting from Sn minus 2 up to Sk. These are these adjacent transpositions. And since you know already this, the representation of this as adjacent, as a product of adjacent transpositions from this procedure using this recursively. So basically, you know how to express any permutation as product of adjacent transpositions. So it has we give a tree-based representation of the construction. So very important thing here to notice is this set for any k. So this pi k we are denoting as I, sk minus 1, and so on. So this consecutive product. So it has k plus 2 elements, I think. And so basically, any sk, like for any k, this sk. So starting from k equal to 2, so for 2 it is pi naught, which is I and identity and s naught. And then for any sk is basically pi times pi k minus 2, where k minus 2 is this one. So this is how you can generate. So this is the algorithm. You can generate all the permutations as product of adjacent transpositions. Now, if you want to look at it, so based on this is very fundamental. That's why we have marked it in using a magenta color. This is very fundamental in this construction. So how do we give this tree representation of the entire generation of the recursive process? You start with identity, and then you fix pi naught, which is s naught and I. So basically, you are multiplying this whatever you had identity with this pi naught, which is so multiplying I with I and I with s naught. So you get 2. And then whatever you have here, so it is basically explaining this. This diagram is explaining this one. And then whatever we have for S1, S2, then you want to generate S3. So what we have to do is we have to take pi 3 and multiply pi 3 with every permutation here in S2. So so you have to multiply this with identity, S1, and S1 times S0. So if you multiply this, you'll get I, S1, S1, S0, and here also you have to multiply this with identity and S1, and then S1, S1, S0. So basically, and these are all the permutations for n equal to 3. Oh, sorry, n equal to 3 here, and then you can n equal to 4 here. So that's how you get a tree-based representation of the permutations. Okay. Now, so from here, if you are intelligent enough, so you can here you can see how to generate a random sampling of permutations, but we'll not talk about it here. So in the quantum context, so we have this transposition, adjacent transposition here. Then we have a quantum state. So when you apply this, so it will be applied on this state. So meaning if we have a quantum state here, when you apply Sj, then this will basically interchange the probability amplitudes corresponding to jth basis, basis element and the j plus 1 basis element. So now, so the question is, what is how do we implement an adjacent transposition in a quantum circuit? So here we see, we prove a theorem that if we have an adjacent transposition, which is even odd type, that means the first one is even and the second one is odd, okay, then it just represents a generalized Toffoli gate. So to give you an example, so let's say n equal to 3, and then even odd means it could be 0, 1, 2, 3, 4, 5, 6, 7. So this is 0, 1, which can be expressed as a Toffoli gate, a 2x gate. It has similar other representations, which also derived from the same decomposition actually. And this is 2, 3, which is this, and 4, 5 is this, 6, 7 is this, and it is in general true. Okay, so yeah, So when we have n qubit system, so we have basically 2 to the power n by n probability amplitudes, and then we can implement this kind of adjacent transposition. And then we can also do this for the odd even, okay, adjacent transposition. So this is a little more complicated. So it is not directly a Toffoli gate, but it's a Toffoli gate multiplied from right and left with the product of like C0 gates, okay, C0 gates, UX. I'm not explaining how do you consider UX. So X is a very special number here, which is this. So when you have this adjacent transposition, let's say odd even, so we are considering this as X and this as 1, okay, because it is odd. So J is odd, okay. So in the bit representation, so there will be n bit representation of J as an integer. So the last bit would be 1 always, and the remaining one is X. So X represents basically the bit representation of X is, it corresponds to an even integer. So X has, let's say, this binary representation, and depending on this X, we'll have this gate UX, which is a sequence of C0 gates. For example, if n equal to 3, so 1, 2, 3, 4, and 5, 6, these are the only adjacent transpositions possible, and this is how it looks like. So here there is only one C0 gate. There are 2 C0 gates, and here is also 1 C0 gate, except that this is a generalized Toffoli gate, which we know how to construct from standard Toffoli gate and C0 gate. Yeah, so we know how to implement an adjacent transposition of 2 different types. One is even odd and odd even. And we know also how to express a permutation in terms of product of adjacent transposition. So we know how to implement a permutation on a quantum register. Okay. Now I'll briefly give you a new. So this is not. So the question is, in the context of the paper, it was random sampling of permutation. So you want to sample permutation from the entire group, but maybe you are interested not. So you are interested in sampling, but not from the entire group, but from a subgroup or a subset of the permutation group. So how to do that? So then we developed a graph representation of the symmetric group. So symmetric group has many different representations, graph representation or combinatorial representation like Kelly graph and mu sigma graph. So there are many representations. So here we come up with a systematic way of generating all the elements of the permutation group through this graph representation based on whatever we have observed and discussed before. So as I said before, pi-k plays a very important role here. So it starts from I, sk, and up to s0 as a product. And then we remove the identity element here, identity permutation. So we denote this new set, which is having, I think, k+1 elements. Pi kg we are writing, and yeah. And then you can take any representation, any graph representation of any discrete representation of this set of k+1 elements. For example, you can consider a connected path, okay, on k+1 particles. You can change this representation. And once we do that, then we show that each permutation group can be obtained from the previous one using the corner product based operation. So this is the generation of the. So this is the representation of S4. This is for S3 and so on.
You have about 3 minutes.
Okay. So I'm almost done. So yeah, these are the complexities of this algorithm. These are all the classical algorithms. And this is the quantum complexity, I mean the gate complexity and the qubit count. So this is our paper, and these are the previous papers. Yeah, so this is the gate complexity. Okay, this is for the random sampling, and this is for the gate for implementing any given permutation. So here are some problems for the PhD students, if you're attending, or if you'll be seeing this later. So as I said, like our graph structure for pi kg is very ad hoc. So we just considered path because it will give me a connect. It's the smallest connected graph, let's say k+1 element. So we consider path and we have some representation, but you can consider different graphs. And when you consider different graphs, you will get the graph representation of symmetric group as a different graphs. And the question is how to relate the algebraic property of the symmetric group with the combinatorial properties of the graph. For example, suppose you have alternating subgroup or any kind of subgroup of the permutation group. Then the question is, what does it represent in the graph? Okay, so how do you associate these things? And there are many nice papers based on other graph representation like scaly graph, and you can do it for this also. And also you can define some random walk on this graph, and you can do permutation sampling. Yeah, so before I end, if you want to see what we are doing, so we launched a 64-qubit quantum computer. So we means here Fujitsu in collaboration with Riken. So in 2023, we had like 64-qubit quantum computer, and then now we have, so which released April 22nd, 2025. We have 256-qubit quantum computer. So this is how it looks like. So superconducting qubits. So there is a freeze and this resides inside a long freeze. Okay, so I'll end it here. If you have any questions, I'll be happy to discuss. Thank you very much.
Thank you. Avishek, do you have anything?
Let's say any YouTube questions if we have. Those who are online mode can directly ask questions.
Yes. Yes, Mr. Vihas. I have heard your mathematical calculation on the topic implementing permutations on quantum device, and very good collection in respect of modern mathematics, in respect of group theory. But I want to know one thing. If you have implied permutations, why cannot we apply combinations on quantum device? Because permutation and combination very close related to each other.
Okay. Yeah, thank you. Thank you for your question. So here by permutation, we are meaning, okay, so that's a good question. So what we are trying to say here is, when you say permutation, so basically you are permuting, the context is you are permuting the probability amplitudes of the vector, and the vector represents a quantum state for some number of qubits, let's say n-qubit quantum state. And when you say combination, that's a so there is a matrix representation of a permutation. Now, so this is the setup that we are talking about. Now, when you say it's a combination, so that is also I would say a combination of certain let's say discrete objects or elements in a certain way. Then the question is, we have to represent this mathematically as let's say, if we can explain it as a transformation, then we have the context here in the quantum. So the question here is, how do you define combination? So as a linear transformation, and if it is, then question would be how to implement this on a quantum register. So we are considering here combination meaning, which is combination of the probability amplitudes, which is defined by a permutation, which corresponds to a permutation matrix. So this is our setup. This is our context.
Thank you. This question will give the idea, the new young researchers, to give the new research paper on this topic. Thank you.
Yeah.
Very good
Sure.
collection and very good work. Thank you. Thank you. Many, many thanks.
Okay, Vivas, I got one question that it's not a question, it's a kind of request. That could you please share the references and the slide maybe? So if you can share with me, I can, if possible, if minutes.
Yeah,
Permissible to
fine.
you?
Perfectly fine. I can share the slide.
Slide and a few references related to that. If that can
Yeah.
be.
So basically, if you this entire material of this, I mean, all the slides are basically part of this paper, which is available freely online. I mean, not this one available, the published one, but there is a preprint version available in archive. So,
Okay, maybe if you can share this link later on, then I can share with the guy who asked this. Okay, and I have seen that there would be like applications of sampling and then random permutations for encryption as well. So recently we are trying to work on a particular field. So there I may discuss with you later on offline, maybe later on.
yeah, sure, I'll be happy to discuss. Thank you.
Okay,
Abhishek.
thank you. Any other further question? If not, then yeah, over to Carl because I don't find any question on YouTube.
Okay. I'd like to thank the Vihas Valedictory for his presentation, and like to call Rohit Sarma Sarkar from Spain. You're here, so
Yes.
again you can proceed.
Okay, thanks. Can you see my screen?
Yes, I can.
Okay. Okay, so before starting, so it's already very late in India, so I'm sure many are going for dinner after this. So this is the last talk. So I'll try to keep it short. So before starting my talk, I want to say thank you to the organizers and thank you to Professor Abhishek Adhikari. We met in Presidency College, my alma mater, and from there we started working on some other problems. So thank you for having me. I am a Marie Curie Fellow at University Politècnica de Catalunya in Barcelona. And today I'm going to be talking about scalable quantum circuits for Hamiltonian simulations and a special case, which is quantum walks. So this talk will comprise of the following parts, which is scalable quantum circuits for exponential or Pauli strings. Using that, we'll apply that to Hamiltonian simulation. For a special case of Hamiltonian simulation, we'll show our results for continuous time quantum walks, and we'll finish the talk. So all of this work has been done with Professor Vibhash Adhikari. Back in the day, he was my PhD advisor, and now he is in Fujitsu. So he may find a lot of things, he will find a lot of things similar. So let us start with the introduction, which is the motivation of designing a quantum circuit model for any system. So the main idea is quantum evolution of a finite dimensional many-body system is described by unitary matrix, and a quantum circuit for us is a unitary matrix, and this quantum gates are sparsely unitary matrices. Hence, quantum circuits are essentially product of sparse unitary matrices, which gives rise to a larger unitary matrix. Now, the idea is how do we represent unitary matrices in a quantum circuit in order to implement them in quantum hardware, like, for example, as Professor Adhikari showed, which is Fujitsu's quantum hardware. Also, it has a lot of potential applications, like in simulation of dynamics of quantum many-body system. It has a lot of uses in healthcare. It has a lot of uses in like finding out folds of protein. It has usage in quantum algorithms and a lot of stuff. So the first result, which I'm going to talk about, is scalable quantum circuits for exponential or Pauli strings and its applications to Hamiltonian simulation. This was recently published in IEEE International Conference on Quantum Computing and Engineering in Albuquerque, New Mexico. And yeah, so before going into the results, so let us review some of the preliminaries. What are Pauli strings actually? So these matrices which you see on your screen, this X, Y, Z, all of these matrices are called Pauli matrices. And if we take a tensor product of this Pauli strings, it forms a chain of these Pauli matrices, which is called a Kronecker product of Pauli matrices. And this chain of this Kronecker product is said to be a Pauli string. For example, if I take X cross Y, it is like a 2-length Pauli string. Similarly, X cross Y cross Z is a 3-length Pauli strings. Okay, now this n-length Pauli string, that is like products of n Kronecker products of all of the possible Pauli strings and the identity, forms a basis of all 2 to the power n cross 2 to the power n complex matrices. So a general idea is, okay, so how can we use this Pauli strings, because we can represent any matrix in complex in a complex matrix and complex matrix in this form. How do we represent them in a quantum circuit or exponential in a quantum circuit? Further, calculating matrix representation of Pauli strings and their exponential is classically challenging, because we are taking, so the dimension is increasing exponentially, right? Because the dimension of the matrix will be 2 to the power n plus 2 to the power n. Now, so perceptible goal is to represent Pauli string exponentials in a quantum circuit in order to bypass larger computations. But why do we need it? We need it because we want to apply this into something called a Hamiltonian simulation. In essence, Hamiltonian simulation is how do we study exponential of a scaled Hermitian operator or a Hermitian matrix in a quantum circuit. So that is, so for the layman, this is called a Hamiltonian simulation. And for example, if H is our Hermitian matrix, which is a Hamiltonian, which describes a lot of properties of the system. It is also used in Schrodinger's equation in a closed system. And a Hamiltonian simulation deals with exponential of the scaled Pauli strings, this like e to the power IH, so exponential of this Hamiltonians. Now, as we said, this Hamiltonian can be written as a linear combination of this scale Pauli strings. So a perceptible goal is if we can find out exponential of this AJ, which is our Pauli strings, by using this, by using a method we'll come to know later, which is called a Trotter product formula, we can determine what will be e to the power minus IHT. Now, Hamiltonian simulation has a lot of application. For example, it is used in simulation, as I said, simulating quantum many-body dynamics. It is used so several real-world problems like stability analysis, or in various medical field also. In many cases, the main idea is to find the minimal, so to formulate the problem in terms of a Hamiltonian and to find out the minimum eigenvalue of the particular Hamiltonian, or known as ground state. So it has a lot of real-world applications. So now, the main idea is, as I said, to write this e to the power minus IHT as a product of e to the power IHJ. So by repeated application of the e to the power minus IHJ using this product, we can approximate up to a desired accuracy of e to the power minus IHT. This is called a Trotter product formula, Trotter-Suzuki product formula. So if we know the quantum circuits of this e to the power minus alpha j hj, we know the quantum circuit of e to the power minus IHT. Now, our circuit should follow certain properties, because in general, circuits, when people talk about circuits, they assume that the underlying structure has complete connectivity, but that is not the true case, because we live in this NISQ era, which is noise intermediate scale quantum era, where not the entire underlying architecture does not have full connectivity. So we cannot just put a CNOT gate in between every single qubits. So it requires a careful planning of where we position our qubits. Also, there is no fixed depth quantum circuits for Hamiltonian simulation. As you can see in the product formula, the depth of the circuit increases exponentially because we have R layers of this product. Also, generally constructing exponential of Pauli strings require computationally cumbersome methods like singular value decomposition, eigendecomposition, or diagonalization, or etc. Further, we want to apply our circuits in a low connected hardware like IBM QX5 or IBM Quantum 2020 or IBM Tokyo, or stuff like that. Hence, the first question is how to construct scalable quantum circuit for scaled Pauli string exponential. A circuit is said to be scalable if given a circuit for n-1 qubit, we can design a circuit for n qubit. So it is like a kind of iterative process. It's like a building on from 2 qubit, 3 qubit, 4 qubit up to n qubit. We can build up iteratively. So that is a very good property of a quantum circuit. Further, can we mitigate the circuit depth for the circuit model of Hamiltonian simulation by constructing scalable quantum circuit for Pauli string exponential? So we need a scalable quantum circuit, we need a low connected quantum circuit, and we need lowest amount of resources. So what do we do? So we do this by establishing a permutation relation between Pauli strings. In other words, we transform a Pauli string into another Pauli string by using some permutation matrices. That's it. So now Professor Adhikari talked about a lot of permutations in his previous talk. So I am also going to talk about a lot of permutations in my talk, but it will be going to be a little bit different. But the core will be more or less the same. So the main idea, first of all, suppose we take a look at this n-length Pauli string. So this I cross I cross I cross I cross I, this n-1 I times I identity, where I is the identity matrix, times an x. This is like an x matrix. So this will always give you a block diagonal matrix of this particular form, where in the blocks of these diagonals, there will always be this x gates or this x matrices. So the main idea is, can we transform, given any Pauli string, can we transform any Pauli string into this particular form? As you can see on your screen, this x can be transformed into that particular Pauli string. And also, what are the permutation matrices exactly? Which permutation matrices converts which Pauli string into which Pauli string? That is also a main issue. It turns out that the permutation matrices we are going to take are nothing but product of disjoint permutations, where each of the components are either both even or either both odd. What are these? I'm going to talk with an example. For example, let us say P24, P68, P810, and it goes on like that. It's like a product of disjoint transpositions, right? So what are transposition? When we say P of alpha comma beta, you imagine an identity matrix and you just swap the alpha and the beta through. So that will give you a P of alpha comma beta. So these permutation matrices will be product of disjoint transposition or two cycles, where either alpha and j are both even, or alpha j is even and beta j is odd. And also they are symmetric matrices, because it's like a product of disjoint transpositions. Now we provide some definitions of what kind of gates we are using. Primarily we are using a variant of CNOT gates, or this some combination of CNOT gates. Why? Because CNOT gate itself are permutation matrices. So we apply our CNOT gates in a strategical way such that we can generate this kind of permutations. How do we do it? For example, let us say we take n is equals to 3 and x is equals to 1. Then what will be the binary representation of x? It will be 0 and 1. So as you can see, at x0 position it is 1, and at x1 position it is 0. So by our definition of pi t ex and pi t ox, you can see that if we put m is equals to 0, and similarly m is equals to 0 here, and similarly j is equals to 0 here, we will get this kind of quantum circuit. So given this pi t ex and pi t ox, we can always find this kind of CNOT combination of CNOT gates, like reverse CNOT gates or normal CNOT gates and stuff like that. Now these are more examples of this pi t ex gate, pi t ox gate, but instead of showing you this, I want to show, this is like a very important theorem which talks about a closed form, like what will be a mathematically closed form of this kind of permutation matrices or this kind of circuits. It is like very difficult to explain in this short talk. So let us start off with an example. I hopefully that will clear a bit of things up. So let us take this example again. If n is equals to 3 and x is equals to 1, we always calculate this kind of expression, like using alpha and beta. like this 2u0, 4u1. So we identify in the binary representation of X where there is 0, where there is 1, and we find out this kind of tables. And using this, the main idea is we will always find that this pi t e of 3.1 is 2p of 2 times 4 into p of 6, 8. P of 3, 1 is p of 2, 3 into p of 6, 7. So what does that mean? You see that these are the product of two disjoint transposition, 2, 4 and 6, 8, where no terms are common. So that's why they are disjoint. And similarly for here. And you see each of the elements like 2, 4 all are 2, 4, 6, 8 all are even. 2, 3 is odd and even. And 6, 7 is again even and odd. So this is the kind of matrices we were dealing with while transforming any particular permutation, any particular Pauli string into this block diagonal structure. These are like some examples of what are the other expressions of these permutation matrices. So I have also prepared an animation for 4-qubit systems on how will this pi t ex and pi t ox look like, this even and odd permutation as we call it. So these are all of the combinations of CNOT gates we are taking into account, and we will use all of these permutation matrices, all of these CNOT gates into our quantum circuit in order to construct exponential of Pauli strings. So before going into that, let us let us give a notation, which is S of Ix is the set of all Pauli strings of length n comprising of only identity and X matrix. And suppose I have a Pauli string as XXII. We always put X as 1 and identity as 0. Then what we will have? 1, 1, 0, 0. This will be a binary string. Any binary string will have an integer representation. So this kind of binary string, so what is the integer representation of 1, 1, 0, 0? It is 12. So sigma of 12 will be XXII. So this is a way of identifying which Pauli strings we are working with. Now comes the most important theorem, which says given any Pauli string comprising of only identity and the X matrix, we can always find this pi t e and pi t o permutation matrices such that they can be transformed into a block diagonal form. So given any Pauli string comprising of identity and X gate can be converted into identity cross identity cross identity cross identity cross identity cross X. So a block diagonal matrix. So this is very significant because any Pauli string comprising of X, Y, and Z can be converted into any Pauli string consisting of only identity and X by using this Hadamard gate and this phase gate or this RZ gate. Essentially, the main idea of this algorithm is to convert any Pauli string first into a product of identity and X gates. Now, when we have the product of identity and X gate, we use our permutation matrix like this and convert them into our block diagonal matrix. And block diagonal matrix, applying the block diagonal matrix in a quantum circuit is very easy. It is like this Rx theta, we can get the exponential of this e to the power plus minus I theta easily. So this is our algorithm which converts any permutation matrix or any Pauli string into a block diagonal matrix and subsequently finds out a quantum circuit for exponential of these Pauli strings. Also, we have calculated, we know how to calculate the number of CNOT gates required for each Pauli strings. Maximum number of CNOT gate required is like around 2n minus 2 CNOT, like this reverse CNOT gates, and 2 normal CNOT gates like from top to bottom, and 2n minus 2 CNOT gates from bottom to top. And using this result, we want to simulate various Hamiltonians which are important in physics, like quantum Ising model, random field Heisenberg model, block diagonal Hamiltonian, transverse field quantum Ising model, and various others. So for example, if we take a block diagonal Hamiltonian, we first find out the exponential of this. We find out a quantum circuit for this matrix exponential, and then using trotterization, we simulate this Hamiltonian, we simulate the e to the power IHT, and we take t up to from 10 to the power minus 3 with e 10 to the power minus 3 steps from 0 to 1 or 0 to 10, depending on the experiment, it varies. But as we can see, that for sparse, so our circuits have fixed depth for 1 sparse and 2 sparse Hamiltonian, which is very important, which we wanted to construct from the beginning. And also, as you can see from the animation which I constructed, that this circuit, that this quantum circuit structure is scalable, because you can always build this structure from the ground up, so which is quite interesting. So we have a scalable quantum circuit, which is also fixed depth for a large class of Hamiltonian. And it also does not require complete connectivity, because as you can see, the only connection between the CNOT gates are this bottom to top and top to bottom, and nothing in between. So this kind of circuits are suitable for star graph architecture or graphs or underlying architecture where the underlying subgraph is like a star graph or a subdivision is a star graph. So it does not require complete connectivity. So this is also quite significant. And we have simulated a lot of Hamiltonians. So for example, quantum, this Heisenberg, random field Heisenberg model, as you can see, the analytical result and the circuit simulation are almost always overlaps. So it is like a good sign for us. Not only that, for transverse magnetic field quantumizing model also, we have done work for higher order trotter. We have done work for long range interaction. So all of these cases, it works perfectly. Not only that, in NISQ era, so there are a lot of noise, there is a lot of error. So we wanted to do a noisy simulation of our quantum circuit, and in order to do that, we incorporated gate error, idle error, beat flip, phase flip, amplitude damping, phase damping, all of which can be written in this particular form, which is called a Krauss operator form, where this EJ, where summation of EJ dagger, which is like a pseudo inverse, will give you identity. And this, like using this gate error, using this idle error, I'm not going into the details of that because our time is short. We simulate our Hamiltonian operators, and we see that the circuit performance is nearly identical to its noiseless counterpart when the magnitude of error is order of 10 to the power 3 or less. So if we can keep our gate and idle error to be less than equals to 10 to the power minus 3, then we are fine. So the circuit is quite robust in that particular case. Also, we have provided a scalable quantum circuit for exponential Pauli strings. No computational cumbersome methods are required. You just need to convert them into Pauli string consisting of X and I, and from there, the algorithm follows immediately. Also, the proposed quantum circuits bypasses the need of full hardware connectivity. It is implemented by IBM QX5 quantum architecture. It has depth for 1 sparse and large classes of 2 sparse Hamiltonians. And essentially, we have provided quantum circuits for matrix exponentials. So it is useful for a lot of things, useful for quantum machine learning, useful for quantum neural networks, and a lot of stuff. Finally, we are going to talk about quantum circuit model for continuous time quantum walk on random graphs. So a random walk is a kind of a Brownian motion. Physics people know it as Brownian motion, but for us, so suppose you toss a coin, suppose it is head, you move right, suppose it is tail, you move left on a particular graph, on a line. So this is like an example of a random walk, but in a quantum walk, unless you measure the particle on a particular graph, so only when you measure, you can say with some probability, okay, this particle can be found at that particular vertex with this kind of amount of probability. So this is the main difference between a classical walk and a quantum walk. It is a universal model of computation, meaning it can be, so any algorithm or any method can be reduced into a quantum walk formalism, and then it can be solved, but that's difficult. It is used in Hamiltonian simulation, it is used in finding marked vertices, it is used in quantum cryptography, it is used in drawing samples for probability distribution, generating probability distributions. But today we are going to talk about this continuous time quantum walk, which is a variant of our Hamiltonian simulation, because where suppose we have a G graph, underlying graph, and a V vertex set, E and H set. Suppose the Laplacian is like the degree matrix minus the adjacency matrix of the graph. Then a continuous time quantum walk is said to be this U e to the power minus IA, such that psi t, so given a starting state which is psi 0, the evolution of the state will be psi t is equals to e to the power minus ht psi 0. So this is a simple version of a continuous time quantum walk where H or Hamiltonian is minus gamma L. L is the Laplacian and gamma is the uniform hopping rate denoting transition probability per unit time between any two connected vertices. So that means what is the probability for the particle to jump from one vertex to another vertex in each time step. So that is the main idea. Now, the system evolves in a Hilbert space because in a dimension of n dimension, representing this with psi state representing the state at a given time t. And the H is spanned by computational basis with each basis state corresponding to the vertex. So we have assumed that the vertex state is V. So in this particular case, if the V is equals to n, so it will go from 0 to n minus 1, 0k to n minus 1k. And the probability of finding the walker at a vertex at given time V is given time t is denoted by this expression, this inner product of ket and this bra of j and ket of like psi of t at time t. Now, a stark difference between random walk and quantum walk is that a random walk generally converges to a stationary distribution, but that is not so for quantum walks, because quantum walks deals with unitary operators, which has norm 1. So it will not converge to a stationary distribution. In order to do that, we define something called a time average probability. And using this time average probability, which is like this limit of t goes to infinity 1 by t in this integration form, we can talk about what will be a time average probability, what will be a kind of limiting distribution of this random walk in a quantum sense. Now, a quantum walk is said to be localized at a given position when the time average probability of finding the walker at that position is greater than 1 by v, or 1 by that number of vertices. So why is it so? So we assume that when uniform mixing is happening in a continuous time quantum walk, each of the vertex has a uniform distribution of finding a probability, equal probability of finding the walker, which is 1 by n or 1 by v. So if a particle exceeds this particular probability, we say, okay, this particular particle is localized at that particular set of vertices or that particular vertex in particular. Now, given a graph Laplacian, what we have done, we partition L into some of these diagonal and block diagonal sparse matrices by repeatedly using these permutation matrices we discussed so far in the previous chapter. And from there, we extract the block diagonal elements, which is very intuitive. So we use all of the permutation matrices, pi t ex, pi t ox, and all of the stuff. And we, by repeated application of these permutation matrices, we extract the block diagonal components. And also, we see that exponential of this IH, where H is a trace zero Hermitian matrix, will always be special unitary. Why? Because people who know Lie algebra will follow from that easily, but we are not going into that now. An interesting result which we have found that our Laplacian partition using a Laplacian partitioning algorithm uses around order of n-1 terms and takes around order of n squared time, where the complete Pauli decomposition of a graph Hamiltonian takes around like this order of n squared log n time and order of n squared terms. So our algorithm is much more efficient than the current existing method. So this is our Laplacian partitioning algorithm, which I explained just now. Just apply this pi t ex and pi t ox all the time in our matrix and just extract the block diagonal elements. And from there, you will get your sparse matrices, and from there you can apply totalization, you can add higher order totalization, and you will be done. So what are the scalable quantum circuits for diagonal matrices? These kind of matrices are scalable quantum circuits for diagonal matrices, where we identify where in the Pauli's chain where there is like I identity where there is Z, and from there we can just draw a C0 gate and our work will be easier. Similarly, we for block diagonal unitaries, we know that this kind of block diagonal unitary is known as a multi-cultural rotation gate, and it has this amount, this kind of like form, and not only that, it is scalable in nature because a lower an n-1 qubit block diagonal unitary used by joining these two C0 gates with this n-1 qubit block diagonal unitary, we get an n qubit block diagonal unitary. So it's like an iterative process to generate like this block diagonal unitary matrices. So by repeated application of this, so again I have constructed an animation and how do we scale this kind of circuits. By repeated application of this, we have our quantum circuit for quantum walks, continuous time quantum walks. So we have constructed our, we have validated our results on these random graphs, which is the Edros-Renai graph, where each of the each possible edge between n vertices is included independently with probability p. So if p is 1, we get a higher chance of getting a complete graph, but when p is less, this kind of like sparse graphs are produced. But anyway, ERG provides a generic and statistically identified graph model, and expected vertex degree is p times n-1, where p is like the probability of occurrence of edge. But anyway, again, we simulate our results, and it's perfect, and it boils down with the analytical result as well. We have talked about localization results, where you see the particle is localized at the starting state always, most of the time, and also it depends on the state as well. But for generic 0 state or generic 1 state, the particle generally localizes at the initial vertex. Why is this localization important? Because when we want to search for a particular particle in a graph, we want to manipulate localization so that the particle localizes at that particular point, so it becomes easier for us to find that particle, right? So what we have done, we have provided scalable quantum circuits for exponential Pauli strings. We have shown application to Hamiltonian simulation. We have shown application to quantum walks. We have done noisy simulation of quantum circuits. As I said, currently I am working in quantum machine learning division at NCCAT at UPC Barcelona. We are hiring, we are taking in PhD students, so please apply, and please find me on Google Scholar. All of these papers are in Google Scholar, ResearchGate, LinkedIn, whatever. So yeah, thank you for listening. And yeah, if there are any questions, I'm happy to answer.
Thank you. That was interesting talk. Abhishek, do you have anybody that has any questions? Or
Yeah, let's see. No, it's very interesting. Some comments are there. Very nice session. Yeah, so no question from YouTube link yet. Let's see. Someone may type it. Yeah, any of those who are in online mode from Google Meet, you may ask some questions. Okay, again, some request I got. Please share your slides if possible. If you share me, I will share it to the concerned person. And Professor Umar Farooq wants to raise his hand. So could you please unmute yourself and
Hello.
yeah, we can hear you. Please go ahead.
Abhishek, actually, I've got a mistake. I've just tapped the button of the hand wave. So that's why it is wrongly done. I sorry for that. I have no question at all, because I have joined late. So the wall that has been delivered here, too much unknown to me.
Okay.
Okay, thank you.
Then, any other question? So if not, then let's thanks once again. And Carl, yours done. So thanks.
okay, so that's the end of this technical session then. So I'll turn it back over to you.
Okay, thank you, Carl. Now we'll very quickly go into our valedictory session. So I just want to mention a few things like those who have appeared for the exam for data science. We can see a lot of people that have already submitted their answers, and those who will be obtaining at least 50% of the score will be getting the completion certificate of the workshop, and those who will be participating this conference significant number of times, like we have circulated periodically the feedback form. Those who have filled up this properly, for them we are going to have this certificate, online participation certificate. And as I just mentioned on the YouTube channel, that it will take some time because we need to sort out things and then we have to prepare the certificate. So as I mentioned, it will be done by 15th of January, but it's to be on the safe side. I took that would be done within this year itself. But to be on the safe side, and regarding the conference presentation certificate. As I mentioned, I requested all the presenters to be present here because I'm going to share the link of the presentation certificate. Those who have presented here, I mean, as usual, like every year, we have very less number of absentee. Here also, we found out of 76 presentation, only 2 of them, they were not present. So except for others, the presentation certificate link would be shared through this valedictory session at the end of this valedictory session. So please, if you find any discrepancy, please let us know so that we can modify it and resend to you. But we have checked it. Our whole team has taken a lot of effort to make it. So hopefully there you won't find any such error. But if anything happened or any mistakes that you find significantly, please point it out so that we can rectify it and send it back to you. Regarding participation certificate, as I mentioned, it will take some time because we have to take care of all the participants who has done significantly. And then we'll send it, hopefully by the end of this year, or if not, then maybe it will take some time to send. But then it's my great pleasure to jump into the valedictory session. And now may I request first the senior most and the youngest, the more energetic person of this whole Olympics, Professor Eric Trell. Though he is the senior most, but mentally he is, I think, the youngest person of this event. So may I request Eric to please start your argument or whatever you want to say. Yeah, please.
Yes, I thank you very much for this fantastic program, and yeah, it's whatever time I'm here, and I'm equally impressed with pace of time in terms of patience and widening the audience by modern technology, and still coming in the quite near format and be able to address personally both, of course, the organizers and the memory of Mahim Adhikari and all nice attenders that appear here. And for me, in this perspective, it's very hopeful to see the new generation coming and occupying these new eras of artificial intelligence. And we also heard about computers development and everything coming into kind of a custom thing. So it will be equally normal to switch on the quantum computer at your home in about 20 years' time, as it is now, to open up this miracle of micros. So it's very joyful and stimulating to be part of this, and I thank you once again for that, and look forward to next year. And yes, thank you so much for this.
Thank you, Eric, for your wishes. And as usual, you stay always with us. And we are fortunate that we are having you as our guide. So you are one of the founder members, founder vice president, founder director of this IMBIC. So we are really thankful to you and all the guidance that you have given to us always. We are also thankful to Christina. We are also thankful to Lena for their constant support, and we wish all the very best to them for the good health and upcoming New Year's. So I think if somebody wants to say something, please raise their hand so that we can one by one call someone. Uh, yeah, so Umesh ji is there, Professor Srivastava. So please say. So he is a very close to our IMBIC, and he is always supportive. And when we have this in our offline mode, he is a very frequent visitor to the IMBIC conferences, and we love him very much. But due to online mode, we are unable to see him physically, but his presence is always there in online mode. So please say something.
Thank you very much. It is my great pleasure and proud privilege to provide my vote of thanks on this auspicious occasion of this memorable international conference organized by IMBIC. And so it is highly honored to me. I myself, Dr. Umesh Kumar Srivastava, having DSC Award in Mathematics, Research Pride of Asia Award in Mathematics, Global Image of Research Award in Mathematics, with my infinite depth of the heart. First of all, I provide my deep sense of gratitude and due respect to our most respectable, appreciable, remarkable, admirable, and most reverent to the founder president of this AMBIC, Professor late Mahim Ranjan Adhikari sir, who had been role model of my research field. While I met him first time in 2006 in 93rd Indian Science Congress conference in NG Ranga Agriculture University, Hyderabad. At that time, he was chairman of the poster presentation of the research paper, as well as Bhola Iswar was the sectional president. On the performance of my poster presentation, he provided me a lot of blessings in the field of research. As a result, today I am DSC awardee. He had been remembered to us up to infinite years among us in this universe, as he was a distinguished, eminent mathematician who made a significant contribution in promoting mathematics, statistics, computer science, really a milestone in the field of research methodology, containing 5 continents and 13 countries of the world and 17 states of our country. I also heartily congratulate on this auspicious occasion to all the dignitary persons and all the participants attended this memorable, successful conference, and especially to my heartily congratulations to Emeritus Professor Eric Trail and Mrs. Lina Trail from Sweden, as well as the distinguished mathematician Carl Sops from USA for their valuable suggestions and informative lectures on this auspicious occasion. Really, it is fruitful for us. Last but least, my special thanks goes to the nucleus of this international conference, to the secretary of this IMBIC, Professor Abhishek Adhikari sir, as well as treasurer Mrs. Minati Adhikari madam, to organize such a beautiful, nice, successful, memorable conference. Really, it is worth praise and highly commendable. Last but not least, I wish all the success of this conference and hope to again meet to each other in our next conference. Thanks.
Thank you, Professor Srivastava, for your nice words, and it's really thankful that you joined us. I think Professor Umar Farooq raised his hand. Would you like to say something? Uh, just 1 minute.
Yes.
So if the participant, if possible, switch on your camera, then we could have a kind of group photograph, if possible,
Oh,
so that we can
yes,
have
yes,
a photograph.
yes,
So
yes,
yeah,
yes.
please, if possible, open your camera.
Yes, I have done it.
Yeah, but not all, so that if
Yes.
all may not be ready at this moment for this camera, but if possible, yeah, many are coming up. That looks good. Yeah, so others, if possible, can join. Okay, more are coming up. It's good. Okay, so yeah, I have taken on, and maybe later on I will take more. So more participants will be joining, and we'll have some more. I will share with you this photograph with you. Please don't switch off your camera now. If you want to say something, it's fine. Otherwise, please stay with us with your camera so that I can take another photograph. Yeah, please, Professor Farouk.
Yes, I have enjoyed it much because this is I think it is the fourth time I am joining this IMBIC, I mean, this conference. It is a pretty well, no doubt. It's a heavy task, huge task of what has been done by Abhishek and his company, especially nonagenarian, Professor Eric Trail, and other who were attached to this program a very success. No doubt at all, it's an awful task, but it is done somehow very successfully. The 3 days where we have on the same platform that we have a journey to the core of the mathematics and also chemistry, physics, computer science, bioinformatics, etc. And not only on the old field, but also in the coming generation, which are actually will be governed hopefully by AI or quantum mechanics, whatever it may be. It is also touched everywhere. That's why we have thrived a lot, and hopefully we'll also meet in the next year in the same time. I have enjoyed it much. I am anticipating its success in the next year, and also in the following year also for this program. And hopefully, I will thanks to all who are concerned to this program, very successful and matured and prosperous. Thank you. Thank you, everybody.
Thank you, Professor Farouk, for your nice words. Yeah, though you might have seen me all the time in front of you, but it's the background actually, those who help me a lot, all my departmental students, the all my research scholars, the departmental research scholars, all the time they help me a lot, and they are still there. We are still at our university. It's around 9:30 p.m. So every day we used to leave from here around 10 p.m. But they are really doing great job. So that you'll be surprised to know that more than 1,000 views have been made on the first day of our show, and the second day count is also going. I'm sure that the third day count would be even more, which will cross the record. It all due to my volunteers, that those who are helping me all the day out, and it's really thankful to them because for them only it's happening. So a great thanks to all of them, and they are all here doing at different machines. So we are currently having a kind of war room situation here. So opening 9 to 10 machines together because we had many parallel sessions, and getting the data, sending that. In that way, I must say that I have already sent to you the money receipt. Those who have paid for that, the money receipt has been sent to all of you. Please check. it might gone to your spam, might be, if you have not yet received, but it might be at your spam. But otherwise, if you don't get this, please let me know quickly so that I can resend them. And regarding the certificate, the participation certificates are not yet ready, but the presentation certificates are ready. I'm going to share with you the link for that, so you can download that. A folder would be shared, and the paper ID is mentioned over there. So please look at your presentation at the program. Paper ID is mentioned there, and the file names are based on your paper ID. So if you just click on your paper ID, you'll see that your name and details are there. If you are going to, for example, I just show you how to open this. I will share with you the link. Maybe I can show you. Can you see my screen? Yeah, so this link will be sent to you. When you open this, you will get this kind of folders. For example, say whose paper ID is 3, that means 3A for 3A might be. If you click on that, it will look like this. So I can increase it. So Eric's signature and my signature are there, date is there. And this is Anand Kumar Misra of whatever institute is there, then state name India, participated this and presented a paper, the title of the paper would be there. So likewise, you can see that all paper IDs are mentioned here. The paper IDs are already there at your program. So please go through the program and you'll find the paper ID and download it. Just click here and then you'll find the download. That's all. And similarly, I will also prepare the participation certificate, and also those who have appeared for the exam. For them also, we'll check how many of you have cleared more than 50. Many of the students, they have, not only students, many of the professionals, they have already joined or they have already appeared for the exam, and their result will also be, the completion certificate will also be sent to them. Okay, so anyone else would like to say something? Yeah, Dr. Nitish Kumar, please. Anything you would like to share?
Come in.
Yeah. Oh, okay. You just made a thumbs up. Sorry, I thought your raise was hands. Okay. Anyone else would like to say something? Carl?
I can't think of anything right now. I've enjoyed the conference. I sat through the whole 3 days and found a lot of good information, and I learned things. So I just like to thank everybody, you, the Trails, all the participants and the people in the background that have made all of this possible. And I'm just happy right now. So thank you.
Okay, the exam link. Someone wants the exam link. Just now I have shared the exam link. It's on the YouTube. Could you please check? I haven't deleted or it's not even gone away. So it's there on the YouTube link. Okay. If I'm going to share here this link for this drive so that you can get this. Please, I'm pasting this on the chat box of YouTube. So please copy this, because at the end of this, you will not be able to access this one again. Let's see if, yeah. So have you seen this? Please copy this, or if you can open this and you can get your direct participation certificate. In the meantime, Graviela, would you like to say something? We cannot hear you. You are muted.
only thank you very much for this conference, for these talks, and see you in 27.
Okay, 26 is in between. So, yeah, surely. Anyone would like to say something? I hope that all of you have received this link. And I have also shared the money receipt to all of you over email. If not, then it's the time to say goodbye and wish you all the very Merry Christmas and Happy New Year in advance. Stay healthy, and we are going to see you soon in the next year because time goes very fast. I just remember that few days back, I did the 18th International Conference. Now I am doing 19th International Conference. For the last 19 years, the same day we are doing it on 21st, 22nd, and 23rd. So in advance, I'm giving you the invitation for the 20th International Conference, Mars 2026. So wish you all the very best and stay blessed and be healthy. Okay, now it's the time to say goodbye. And I must say thanks to all my scholars, all my students, all the persons in my department who helped me a lot to make it a success. Thank you. Thank you for all your cooperation.
Thank you. Thank you.
Thank you.
Thank you.
Okay.
Thank you.
Okay, then it's the time to say goodbye.